So we'll start at 10:30, right? Kiran sir?
Yes, sir. No, sir. We will start at 10:30. We are just waiting for the participant.
So shall I, Dr. Kiran, shall I share the slide right now, or I'll wait for?
Yeah, you can share, sir. You can share. You can share.
Yeah, you can share this slide.
You can share your slide.
So I'll just show the first slide.
Yeah, but this one is fine, sir. We will see that because 10:30 it will start at YouTube also. So I will check whether it is streaming started or not.
Okay.
So, Dr. Vishwas, how is it in Bangalore? How are the things going on there?
Yeah, things are good. Like our institute is fully functional now, but a few students yet to come back. But most of the students came, and all over city now it's crowded again. It's back to the normal, but cases are like kind of in the range of 3,000 to 4,000 every day. But people are used to now.
But I think now it is on the downward side of the curve, I guess.
Sorry?
It is on the downward side of the curve right now, I guess. Is that true?
Yeah. It's not downward yet in the city, so it's not very downward. It's flat, you can say,
okay.
But still not downward in Bangalore.
Okay. Yeah, one of my friends was at JNCSR, Dr. Abhay Sagade. Have you had any connection with him?
No. But what is his name? Abhay
Sagade.
No, I don't know him. No. Which department? Is a student or a postdoc?
No. He was a postdoc previously, from I think 7-8 years back.
Okay.
Even before that, I guess. Yeah.
Which department?
I don't actually remember his department because it has been long. And yeah, I thought maybe you had some. He was working on graphene and things like that.
Okay.
So he was at Cambridge later on, and now he has joined in some Tamil Nadu SRM Institute at Tamil Nadu.
Okay. If I see him, I'll recognize, but maybe he's from other department. I don't know his name.
Yeah, maybe.
This was me and Sundaresan first student, Bentes, Kumar Mangalam.
Yeah.
We were together in France, in Dismat. We both were doing postdoc together.
Okay.
So I think he also joined recently in SRM. He joined SRM.
Yeah, Venkatesh I know very well.
And Claudia was also there. So we have many people from Bangalore.
Okay.
Claudia also did PhD from Bangalore.
Right, Claudia is a very good friend of mine. Like I don't.
Yeah. He told me that you used to play together or discuss together.
Right.
Claudia was there. Ranjit was there.
Yeah.
And we had a good association actually. That time in France, Christmas, Wilfried want Indian only actually.
So Christmas, I have very good association now because one of my student is also there now.
Oh, with whom? Sylvie or with Antoine?
No, it's not Antoine. He's with Gilmo, Emmanuel Gilmo.
Oh, Emmanuel Gilmo. Okay. So they are working together. Yeah. Great. So in Christmas, we have very good Indian association.
Okay.
So every time you will find one or two postdocs most of the time.
Right.
Okay, so shall we start actually? Participants are also more than 80, so we can start, and it is also live on YouTube.
Yeah.
So thank you, sir. I welcome you. Thank you very much to accept our invitation to be the part of this short-term course on energy material. So now, Vedehi, please continue. She will introduce you. Vedehi, please.
Yes, sir. Am I audible, sir?
Yes.
Am I audible?
Please continue. You are audible. Please continue.
So very good morning to each and everyone present on this platform and on YouTube today. I am Vaidehi Deshmukh. I welcome you all on the third day of short-term course on advanced energy materials. After the interesting talks about renewable energy, lithium batteries, piezoelectric and magnetoelectric devices, I'm sure you all are very much excited to attend today's talk. Ladies and gentlemen, energy is the most important aspect of our life. and intelligent use of energy for the benefit of mankind is a need of 21st century. As no system has 100% efficiency, a lot of energy is wasted in the form of heat. Now imagine if you could use this heat to make electricity. Thermoelectric materials are the way to do that. Our today's talk is going to be on the thermoelectric materials by Professor Kanishka Biswas from JNCASR Bangalore. It is a great honor to introduce our today's guest. Ladies and gentlemen, Professor Biswas is an associate professor in Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. He obtained his PhD from Indian Institute of Science, Bangalore. He did his postdoctoral research in USA from Northwestern University. He is a recipient of various awards, including Material Science Annual Prize by ICSC, MRSI. He is also a recipient of Swarna Jayanti Fellowship from DST in 2019. He won a bronze medal from Chemical Research Society of India in 2019 and a medal from Material Research Society of India in 2017. He is also recipient of Wiley Young Scientist Award in 2017, Young Scientist Medal from INSA in 2016, Young Researcher Merit Award in 2016, and Young Affiliate of the World Academy of Sciences in 2015. Sir has published around 150 research articles, 2 books, and 7 book chapters. Sir has 3 patents and more than 11,000 citations. He is an associate editor of American Chemical Society Applied Energy Materials from 2018. He is serving as advisory board member of various renowned journals like Journal of Solid State Chemistry, Journal of Materials Chemistry, and iScience. His area of research and interest is solid state and inorganic chemistry, thermoelectrics, 2D materials, topological quantum materials, and perovskite halides. I am very much grateful that Professor Biswas is here with us, and I extend a very warm welcome to you, sir, and I request you, sir, to please enlighten us with your talk. Sir, please.
Thank you very much. Thank you, Vaidi, for a very detailed introduction. And I thank NIT Jalandhar for inviting me, especially Dr. Kiran, for inviting me and giving the opportunity to show some of our recent results. But before that, today I'm going to talk about the fundamental of thermoelectric energy conversion, and then there onwards I'll go towards details of our results in this thermoelectric energy conversion. And I belongs to New Chemistry Unit and also International Center for Material Science, and under the umbrella of School of Advanced Materials. So we have very like strong materials advanced material program in JNCSR, and I'm sure today afternoon you will see another speaker from the same.
Eco is coming.
Sorry.
Eco is coming, sir.
Sorry.
Eco is coming, sir.
Eco is coming.
It's
So
all right, actually. Maybe I request all the participants to please mute yourself to avoid any disturbance. From our end, it's fine.
Okay.
Yes, sir. Sir, continue,
Fine,
sir. Please.
So you can continue.
Yeah. So now what is thermoelectrics? So thermoelectric is a direct conversion of temperature difference to electric voltage and vice versa. So it's divided in 2 effects. One is Seebeck effect, another one is Peltier effect. So these two, for example, Seebeck effect is discovered exactly 200 years back. So what is that effect? As you know from your class 11 or 12 physics or chemistry, if we create temperature difference, hot end and cold end, P and N type semiconductor actually can generate voltage. But please remember, P and N type semiconductor are the solid state material, or they are connected in a electrical series, but thermally parallel. That means hot and cold should be thermally parallel, but electrical in series, and this can generate voltage. But in Peltier effect, we provide the voltage externally, and this same setup device geometry, this solid state inorganic semiconductor, can generate temperature difference, and this temperature difference, hot end can be near to the room temperature, and cold end can be the active cooling end, which can be used as refrigeration. And these Peltier coolers are known for long time, and you can see the products are there based on Peltier coolers in the market for last 30 to 40 years. Okay, so we have Peltier cooler fridges, and there are many scientific instruments which has Peltier cooling because it can be used for spot cooling and many important uses. But today I'm going to talk about mostly about Seebeck coefficient, which can generate temperature difference to electric voltage. So how the real thermoelectric device looks like? The real thermoelectric device will look like this. This is in centimeter scale, and you can see there are several P and N type relay connected in electrical series but thermally parallel. So this is a real thermoelectric device. So now I'm going to show one video where we have, and this video has been done actually in my lab, and this is one of my PhD student. Akashmi is doing this experiment. We have ice cold water in a beaker, another beaker she is going to put hot water, and this is a fan connected with a motor, and then we have here the thermoelectric devices. So let's see what happens. Okay, so this is cold water, and then Akashmi is putting hot water here, and we have a fan with motor, and we have a thermoelectric device. So this white thing you can see, that is the thermoelectric device actually in our lab. Okay, let's see what happens. So cold water temperature, ice cold water temperature is close to 10 degrees centigrade, and the hot water temperature is close to 70 degrees. So we have around 50 to 60 degree temperature difference, and from the temperature difference, actually we are, this is generating electricity, and actually it can run the fan. So you can see the power of this technology. So let's see what is the importance of thermoelectric, why we should do research in thermoelectric not only in India but also in world. So if you see the total energy consumption in India is 2018 and world is 2018. So we consume in terms of energy in terms of coal, petroleum and natural gas. Okay, so please, this is a note, this is an energy consumption curve, not energy production curve. So we use combustion of coal which generates electricity, and combustion of petroleum and natural gas which actually generates energy for the transportation and commercial uses. But we only use 35% of this energy by combustion of coal and petroleum and natural gas. 65% of the utilized energy rejected as a heat. So what do we do with this waste heat, right? So can we think now this waste heat end can be the hot end of the Seebeck coefficient, and we have the efficient P and N type semiconductor created in our lab, and this cold end can be lower temperature or near to the room temperature, and this waste heat can be converted now to electricity by thermoelectric energy conversion. So that is the main motivation to do work in this area, because we can convert around 20% of this waste heat to electricity by this thermoelectric energy conversion. So what are the uses? So it can be used for direct heat to electricity conversion, where waste heat recovery in power generation. In large scale, it can be used in power plants, in any kind of power plants. I'm talking about chemical, thermal, nuclear, and steel. If I have get time, I'll give a example of steel power plant. And in medium scale, it is already in use in automobiles, but this has been done in the technology has been done in the high-end car companies like BMW, Ford, GM. They have installed thermoelectric generators in the exhaust pipe, because exhaust pipe we lose 70% energy as a heat, and this energy can be heat energy can be converted back to electrical energy, and this electrical energy can charge a battery in a car basically, and then that means you have to have a hybrid car, and this will make this car or automobile fuel efficient. Okay, so now. And the next application of this thermoelectric technology is basically space power generation. So this is very interesting, and this space power generation actually given the huge motivation to use thermoelectric materials for waste heat recovery. So this technology is known for NASA or JPL Caltech. NASA has a collaborative project, and also as in Russian Space Foundation for last 35 to 40 years, because they have used this technology in their many deep space mission to power the spacecraft. So now you can ask me question, why you need to power the spacecraft by thermoelectric technology? Because if you are having a mission like say deep space. For example, we are going really far from sun, so efficiency of the solar cell decreases heavily. For example, how to power the spacecraft that time and how to power the electronics so that it can take photograph, it can send data to Earth. So in order to do that, what NASA scientists did, so they have taken radioactive elements such as plutonium-238. So they have taken basically plutonium oxide. So plutonium oxide in a seal tube, and this plutonium oxide decays at least for 28 years, because the half-life of the plutonium oxide is 28 years, and provide the heat of around 300 to 350 degrees centigrade. And this is encapsulated in the seal tube, and the jacket of the seal tubes are actually made by this thermoelectric generator. So these are all thermoelectric generators, and that can actually convert this heat from the radioactive decay to electricity and power the spacecraft. And they have used this RTG, radioactive thermoelectric generator, for many missions, for deep space missions like Apollo, Pioneer, Viking, Voyager, Galileo, Cassini. So they have huge number of missions. They have used this thermoelectric technology. So, and that actually given the motivation, these thermoelectric materials can be used for actual power generation in waste heat in power plants and also in the car exhaust. So what are the new uses of this thermoelectric power generation? One is solar thermoelectric. I'm sure that somebody has given or going to give a talk on solar cell. But in solar cell, actually, we convert like light energy to electricity, right? But we have huge amount of heat part of the solar, that IR part of the solar. So how to convert that heat part? So now if we combine this solar and thermoelectric together, so basically installing thermoelectric generators down the solar panel, actually this can make the system much more efficient. So you will have together solar thermoelectrics. Now, all of you have mobile phone and laptops nowadays, right? So you can see if you talk for like say half an hour, or if you charge or laptop or working for laptop for longer time, the lithium-ion battery heats up, right? So that can be, that waste heat from the battery can be also converted to electricity by this thermoelectric generator if we make it together battery plus thermoelectric. And this is for a not for a small use, but because our government is thinking electrical mobility soon maybe, and this car will be car energy will be replaced by actually battery, and this battery will heats up again, and you need to have that time thermoelectric generator with battery technology to convert this waste heat from the battery. And then another use of this thermoelectric power generation is basically heat recovery from data center. Because data center is getting importance day by day heavily throughout the country as well as in the world, because we are generating huge number of data, but data center, if you go and check, it heats up enormously. So how to recover waste heat from the data center? So there are several motivations to work in this field to make efficient thermoelectric material and devices. So I'll show today some of the examples, but we should not forget about the other part of the thermoelectrics, that is the cooling part, that is the Peltier part, which is known for last 40 to 50 years in the form of products. So we can have commercial cooler warmers, spot cooling, microprocessor, laser diode, and also several scientific instruments have this cooling. So now I move on to basically the fundamental science. What is the chemistry or physics behind this field? That we have to talk about the materials property or thermoelectric parameters. So thermoelectric figure of merit is defined by this equation. So this is a dimensionless thermoelectric figure of merit, so that we can compare material A to material B, which will have high ZT, that will have high thermoelectric efficiency. So the numerator of the equation is Seebeck coefficient. This Seebeck coefficient is nothing but how much voltage per unit temperature difference one material generates. Okay, so this is the Seebeck coefficient, delta V versus delta T. The unit of the Seebeck coefficient is generally microvolt per Kelvin. So this is purely a material property, and this is a property of a semiconductor. So now another property in the numerator of the ZT is sigma, which is electrical conductivity. I think all of us know what is electrical conductivity. That means how charge flow from one end to another end of the material. Charge means electron and holes flow one end to another end of the material. So now let's talk about the denominator, which is nothing but thermal conductivity. So thermal conductivity means how heat is flown from one end to another end of a solid. So this we have to have low thermal conductivity. That means low denominator value to have high ZT, whereas we have to have high Seebeck coefficient and high sigma to have high ZT. So this thermal conductivity has two parts. The first one is electrical thermal conductivity. So electrical thermal conductivity is nothing but like how electron and hole carries the heat. For example, if you put a copper wire in a fire, automatically you get a thermal shock, and this because copper is a metal, so metal will have high thermal conductivity because of it has hole and electron, and this electrical part of the thermal conductivity is directly related to the sigma by famous Weidemann-Franz law. So basically this is the relation L sigma T. So sigma is the electrical conductivity, L is the Lorentz number, and T is the temperature. So we don't have much control on the electrical part because we want high electrical conductivity. That means this part of the thermal conductivity, that is the electrical part of the thermal conductivity, also will increase. But another thing which carries the heat is basically phonons. So I'll come in a minute what is phonons. So that is called lattice thermal conductivity, and this lattice thermal conductivity is the only independent part in this equation because electrical part of the thermal conductivity is related to the electrical conductivity by famous Weidemann-Franz law, and Seebeck coefficient and the electrical conductivity are related by carrier concentration and related by the Mott equation. Okay, so now the only independent parameter is basically lattice thermal conductivity. So today's talk I will going to give the example how we can modulate this lattice thermal conductivity, that means decrease the lattice thermal conductivity to increase ZT. So the fundamental challenge in this field is basically if you see this upper part, the numerator is basically related to the electronic structure of the material, and lower part is basically the thermal transport. So basically we have to do decoupling of electronic and thermal transport in a solid material to have a better thermoelectric. So now I see this problem in a slightly different fashion, which is I feel is interesting in perspective to the students. So we know glass is very bad thermal conductor. So that means we need a bad thermal conductor, property of glass, property of metal, which is a good electrical conductor, and property of semiconductor, which is a good Seebeck coefficient. So now this is a real challenge in this field. You have to have a solid inorganic material which will have property of glass, property of metal, and property of semiconductor. So developing new material in this field is extremely challenging, which will have property of glass, metal, and semiconductor together. So if you can have a property of three important parameters, you can actually develop good thermoelectric material. Okay, so now, so I am a solid state chemist. I again see this problem from a chemist perspective. And this is very simple way to think about it. So basically, if you all we know about periodic table, right? So if you go down the periodic table, like for example, from metal oxide to sulfide to selenide to telluride, the band gap decreases enormously. For example, oxides are generally insulator, but if we go to the telluride, the band gap values are basically below 0.5 electron volt. This is really low band gap values, and even the state of art material in this field are having the band gap around 0.1 to 0.2 electron volt. Okay, so we can decrease the band gap, and as you can see by simple molecular orbital diagram, this is metal, and this is for example anion. And this valence band have the anion character because this is close to the basically anion, whereas the conduction band has the metal character. So now if we go down the periodic table, electronegativity decreases. So automatically this orbital goes up, and we have decrease in the band gap. So that's why the band gap decreases. And if we have a very low band gap, actually that works like a semi-metal. If we dope heavily, that works like a semi-metal or degenerate semiconductor. We can have very high conductivity as similar to metal, but still we have a band gap. So it will have a reasonable Seebeck coefficient. Now you can think basically if we are going down the periodic table, we will have heavy elements like lead, tin, selenium, tellurium, and we construct the lattice, crystal lattice by heavy elements. So automatically the lattice vibration slows down. That means phonon vibration slows down. I will tell you in a minute what is actually the phonon for students. So once we have slow phonon vibration or less group velocity of phonon, will have glass-like thermal conductivity. So all these three properties like glass, metal, and semiconductor converge down the periodic table. So today I'm going to show some of the example. We have made new material from this in this field from this down the periodic table, which will have all these three properties, and that is one of the important logic to develop new thermoelectric material which taking elements from down the periodic table. Okay, so let's see what are the state of art thermoelectric material. This is ZT versus temperature versus which year the materials are discovered. So I divided this plot in 3 generations. ZT below 1 we call first generation material, which are generally discovered before 2000, and then ZT 1 to 2 they are discovered 2000 to 2012, and the third generation material just which are having the ZT just above basically 2, and this is the first material, bulk material, which has ZT around 2.2 cross first time this third generation material. Okay, and this, if you see this curve, this all the materials like are based on, not all, like most of the materials are based on lead. So the another important challenge in this field, basically you have to have lead free high performance material for mass market application. So now so how we make the material in our lab? We have significant expertise to make these heavy metal based chalcogenides either by polycrystalline fashion in seal tube reaction. Then we can do ball milling and spark plug sintering. We can make nanomaterials by slackline, and also we can do single crystal growth by Bridgman furnace as well as dual zone furnace by vapor transport reaction. So we have significant expertise about synthesizing this material by different means. So let's see. I go back to the thermal conductivity. The lattice part of the thermal conductivity is basically phonons. So the phonons are basically lattice vibration, crystal lattice vibration, which are quantized as similar to electron. So these phonons, which are having the wavelengths around 1 angstrom to 100 nanometer, carries the heat. So now there are 2 types of phonons. One is acoustic phonon. Acoustic phonons are nothing but the sound waves. So this acoustic phonon actually carries the heat in a solid material, and we need to actually scatter those acoustic phonon. Okay, so this acoustic phonon is, again I'm telling, this is related directly to the sound velocity in a solid. So now there are another type of phonon which is called optical phonon. And optical phonon actually we can determined by spectroscopic techniques such as Raman spectroscopy, terahertz spectroscopy, or IR spectroscopy. So in acoustic phonon, all atom vibrates in same direction. Okay, but for optical phonon case, that the different atom vibrates in different direction. So it creates dipoles. We can determine by optical spectroscopy technique. So now for a simple solid, there will be always gap between optical and acoustic phonon. Okay, so please remember that there will be always a gap. So now what we have to do, we have to actually scatter this. We have to block this. Some way we have to block this acoustic phonon. Okay, so that is the goal, and this acoustic phonon wavelength is generally 1 to 100 nanometer, 1 to 100 nanometer, which actually carries the heat. Okay, so now there are important concept in this field how to actually scatter those acoustic phonon. So initially Russians started this work. So they have actually made this solid solution point defects. So that that can only scatter the phonons which are in angstrom scale wavelength. So those phonons actually does not carry that much heat. But if you see in this heavy metal based telluride, which carries the heat, are in the range of 2 to 20 nanometer. So we have to have similar object to scatter those phonon, and these similar objects are basically nanoprecipitates of similar size 2 to 20 nanometer and embedded in a solid matrix. So if you are working in, for example, lead telluride or bismuth telluride, so this is a lead telluride matrix. This whole is lead telluride. Basically, this box is lead telluride, and these nanoprecipitates are something which and the size of 2 to 20 nanometer, which actually can scatter that phonon. And you can see this is actually a very important field in thermoelectric, nanostructured bulk thermoelectric. So if you see, this is the lattice thermal conductivity. This is experimental data of PVT. PVT is the champion material in thermoelectrics. So when they have done the solid solution 60-70 years back, they see a sudden decrease in the thermal conductivity because of this short wavelength phonon scattering by point defects or solid solution. But first, this paper in Science in 2004 from Michigan State by Kanazidis group, they actually discovered this material first time, last 18. So this is basically PVT matrix, and they have this AGHB nanoprecipitates, and these nanoprecipitates are in the size of 2 to 20 nanometer, which can scatter the phonon heavily. and then decrease the thermal conductivity almost to the glass limit, and that actually paper created the field of nanostructured bulk thermoelectric. And there are several important papers came in this field in different material, integrating point defects, nanoprecipitates, mesoscale grain boundaries, which can scatter phonon heavily. And we have also contributed significantly in this area from India. So now you can ask me question like, okay, this nanoprecipitate can scatter phonon. Okay, so basically this nanoprecipitate can scatter phonon heavily and decrease the thermal conductivity significant amount. But at the same time, this nanoprecipitate will have dislocations, so it will scatter basically electron and holes. So we'll have slight decrease in the electrical mobility, and this electrical mobility is directly related to the electrical conductivity. So we'll always have a decrease in electrical conductivity in a solid material which has this nanostructured precipitate embedded in the matrix. So we are compromising with the electronic transport while decreasing the thermal conductivity heavily. Okay, so now this approach is more like an engineering approach, materials engineering approach, where people do nanostructuring, point defects, as well as mesoscale grain boundaries. And this approach we call, this is the extrinsic approach, because we have introduction of foreign point defects, nanoprecipitates, and grain boundaries. Okay, so now today I am going to talk about this intrinsic approach. So that means we will not do anything, like we will not do any nanostructuring, we will not do any mesostructuring, but still the thermal conductivity can be decreased, because this intrinsic approach is practical interest, because it has a robustness against grain size and temperature, because this, if you increase the temperature, wherever you have to actually use this thermoelectric material. So basically nanoprecipitate can dissolve in the matrix, and this phonon scattering may not work. So we have to have material which are intrinsically low thermal conductivity. In order to do that, we have to actually basically modulate the chemical bonding, more fundamental parameters and lattice dynamics. Okay, so let's see. First example I'll give is basically excuse me. So basically this compound thallium Fe, which is worked by my PhD student Moinak Dotto. So this thallium Fe is a very interesting material discovered in our lab, which shows ultra low thermal conductivity, basically around 0.4 watt per meter Kelvin at high temperature, whereas 0.6 watt per meter Kelvin. And you see this sample does not have any nanostructuring or mesostructuring. This just made a ingot format, or if you can make single crystal format, and you measure the thermal conductivity, you get this value. And this has one of the lowest value reported in this family, and this is much lower than the state of art material. So what is happening here? Basically, okay, so we have to understand what is happening in this thallium Fe, and this is intrinsically low thermal conductive material without doing any grain boundary engineering, nanostructuring, or point defect engineering. Okay, so in order to do that, we have to understand the structure of the material significantly. So don't get confused with this complicated structure. I'll tell very simplified way right now. So this thallium Fe, basically, if you see, this selenium is 2-, okay, but thallium cannot be +2. So this +2 oxidation state of thallium is not feasible. Okay, so that means thallium has to be +1 and +3. That means thallium +3 and +1, which is a mixed valence system. So that is the main motivation we choose this compound, because thallium +1 has a 6s2 lone pair. Okay, now, whereas thallium +3 doesn't have a lone pair, and this thallium +3 actually form this shorter bonding with tellurium, this covalent tetrahedra. You can see tetrahedra, and this tetrahedra runs like edge sharing fashion and form this one-dimensional chain type of structure. Whereas thallium +3 sits in this channel, and it has longer bonding, weaker interaction, so it has an ionic interaction, and this thallium +3 has a lone pair. Okay, so that is the trick in the structure. So we have created a stronger bonding, okay, and we have created a weaker bonding, that is the ionic bonding. You can see the length is higher, and this, while creating this bonding hierarchy, basically we have created this thallium +2 in the channel, thallium +1 in the channel with a lone pair, with a spherical lone pair. Okay, so now what is our hypothesis or intuition was basically this thallium +2 actually thallium +1 with a 6s2 lone pair actually rattles in this channel, so they move around. because they are connected with weaker bonding, so they move around, and this moving around will give low energy optical phonon. So please remember this curve I showed. I go back here. So basically we get this optical phonon in this material is here. Okay, so once we decrease the optical phonon energy by this rattling event, actually it couples with the acoustic phonon, and this optical phonon actually scatters this acoustic phonon. So that was our intuition. Okay, so this, can we prove this rattling of this thallium +1? So in order to do that, we have calculated the electronic charge density and electron localization function. And electronic charge density clearly says that basically thallium +3, this is +3, this one basically +3 has nice electron sharing. You can see this is a nice covalent bonding, whereas thallium +1 has a spherical lone pair, and this lone pair with the lone pair in ionic interaction, it sits in the challenge. And then now when we have calculated the potential energy tells you about the bond strength, and this potential energy is flat for thallium +1, the blue curve. So that means it can actually rattles perpendicular to this slide, and this rattling can give rise to low energy optical phonon modes, which actually scatters acoustic phonon modes. So now I collaborate with Professor Wagmorev, which is a renowned theoretician from our same institute, who has calculated the phonon density of states, and you can see these three are the acoustic phonon, 1, 2, and 3. These are the acoustic phonon, but we have very low energy optical phonon, and this low energy optical phonon actually couples with the acoustic phonon, which actually gives rise to this low thermal conductivity in this material. And when we plotted this partial phonon density of states, the low energy phonon modes, these EG modes, basically are coming from this blue atom, which is nothing but the thallium +1. So that proves that this thallium +1 actually rattles in this channel and give rise to these low energy optical modes, and which actually scatters this acoustic mode. And we have calculated this Gunness-Hahn parameter. So Gunness-Hahn parameter is nothing but basically enharmonicity, how much enharmonicity is, the system is having. So the value is quite high. So that suffices that basically this system has intrinsically low thermal conductivity. So now after our structural analysis, chemical intuition, and theoretical calculation, we are a bit sure that basically we have these rattling modes, but how to observe those rattling modes experimentally. Okay, so we have done low temperature heat capacity measurement. So don't worry about all this equation. I'll simplify in a minute. What we have done, this is the low temperature heat capacity data. Low temperature means we have done 2 to say 50 Kelvin, because this is in square. Okay, so we have done really low temperature heat capacity data, and this, as you know, because most of the people are from physics background here, I guess. So people must be knowing, also from chemistry background, people must be knowing this heat capacity follows this d by t cube law, right? D by law, right? So now if you see this heat capacity cannot be fitted by d by model. Okay, so simply t cube law cannot fit this heat capacity. So basically we have to invoke Einstein. This is the Einstein mode in this equation, because if I take this t in this side, so this is basically t cube loss. We have to have combined d by, this is the d by part, this is the electronic part, and this is the Einstein part. So we have to include in the equation Einstein part, and this that actually fits the heat capacity. So what is Einstein part? So Einstein assume atoms as a single rattler. Okay, so each atom has a rattler, which is there in a solid d by lattice. Okay, so when we have included this Einstein part in this heat capacity equation, actually this data is fitted well. So that tells about the optical phonon modes. We see the wave numbers, very low energy, 15 centimeter, 30 centimeter, and 51 centimeter. Got it from heat capacity data. So these low energy optical phonon modes are actually coming from the thallium rattler. So this is the direct proof by experimental means. This actually thallium is rattling in the channel and gives rise to low energy optical phonon modes. So now more sophisticated way to do analysis. Basically, if you take Cp by Tq versus T, that shows a nice hump. And this hump is basically boson-like hump. So boson, you know, it's coming from Indian scientist name, Satyam Bose. Okay, so this boson-like hump actually gives rise to excess optical phonon density of state in this material, and this boson-like hump are generally observed in disordered glasses. Okay, so that also tells about this low energy optical phonon modes. Okay, so this is a bit complicated analysis. So now can we see, as I told you, this optical phonon mode can be seen by spectroscopic technique, right? So can we see this thallium rattler mode by spectroscopic technique? So I have very good collaborator. One is Pankaj Mondal from ISR Pune, another one is Vijay Soni from IIT Mandi. So Vijay Soni has very good Raman setup, who has basically low energy filter in the Raman, and Pankaj Mondal is expert in basically terahertz spectroscopy. And this, if you do the space group analysis, so this is a centrosymmetric space group. So you should see basically rules of mutual exclusion. All you read in your BSc or MSc classes. So basically some of the mode will be IR active, some of the mode would be Raman active. So terahertz is complementary to IR. Okay. So actually, if we do group theory analysis, we should see this many modes, and some of the mode will be Raman active, and these are the EG mode, which we have done the calculation and showed, and this EG mode actually coming from this thallium rattler, and we have shown directly from the spectroscopy this EG mode, and from the terahertz you can see again A2 and EU mode. So basically we have established this thallium actually rattles in the channel and give rise to ultra low thermal conductivity in this material. So what is the message we should get out of it? So basically, if you remember, I go back to the structure. Basically, we have created by chemistry, solid state chemistry, strong bonding framework, that is the covalent substructure, and weak bonding framework, which is ionic substructure, which is related to this rattling. Okay. So what we wanted to do here, basically this covalent bonding framework, which is a strong bonding framework, makes the basically the valence band or conduction band minima, maxima or minima. So that actually takes care of this electronic transport. Okay. Whereas this ionic or weaker bonding framework takes care of the thermal transport. So basically, we have decoupled the numerator and denominator of the ZT into different sublattices. Okay, so that means electron or hole can be transported by this strong bonding framework, whereas the phonon can be scattered due to this weaker bonding framework, where we have this rattling phenomena. So this is one of the examples which is created first time from our lab, and of course this has many implications. So you don't have to do mesostructuring and nanostructuring. So I'm audible, right? Clearly? Hello? Am I audible clearly?
Yes, sir, you are audible.
Yes, sir. Everything fine, sir.
Okay, good. So I'll just, I'm not getting any response. So I thought, and feel free to ask question if you have any question. Okay, in between also. Yeah. Okay. So then so we move ahead, and we wanted to prove much more, wanted to show much more examples where intrinsically low thermal conductivity in an inorganic solid. In order to do that, we started working in lead-free system, which is tin telluride, and this tin telluride has exactly similar structure to lead telluride. So what is the lead telluride structure? You can ask me. So this lead telluride structure is basically sodium chloride structure, and this sodium chloride structure, as you know, is basically very basic structure in solid state physics and solid state chemistry, is basically interpenetrating face-centered cubic. So this interpenetrating word is very important because there are two face-centered lattices. One is chlorine, and another one is sodium, which are generally interpenetrated. Now, if we replace tellurium by chlorine and sodium by tin, this is basically tin telluride. Okay, so this is a face-centered cubic structure, and this has similar electronic structure as lead telluride, although there are some differences today. But today I am not going to talk about electronic structure modulation. I will be focusing mostly on phonon transport or thermal transport in a material, and we have shown basically tin telluride is a good thermoelectric material. Before we started working in tin telluride in 2013-14, tin telluride was kind of neglected by thermoelectric community and the solid state community, because tin telluride have several drawbacks, but it has similar structure and similar crystal structure. So we thought tin telluride will be good material. Actually, we made a good material out of this tin telluride, which was published in 2016 by electronic structure modulation. But as today I'm going to focus about only thermal conductivity. This is the thermal conductivity of this pristine tin telluride without doping, mesostructuring, nanostructuring. This tin is sourced from value 3 watt per meter Kelvin and goes around 1.2 watt per meter Kelvin. So now we can calculate K theoretical minima for each solid if we know about the sound velocity, because as I told you, the acoustic phonon carries the heat. So this acoustic phonon directly relates to the sound velocity. So if you know sound velocity, we can calculate that, and we know this Boltzmann constant as well as volume of the from the crystallography, and then we can calculate the K minima, which is 0.5 for thin telluride. So now please notice, if we can get the thermal conductivity from here to here, so that means how much we can improve the ZT in tin telluride. So when we started working on the thermal conductivity of the tin telluride, the value was still in 1. Okay, it is here basically, somewhere here at high temperature. Okay, but room temperature there was not so decrease. So in order to do that, what we have done, as I told you about this phonon spectra, we have seen the paper, old paper of tin telluride, and we have seen this tin telluride has a face-centered cubic structure at room temperature, but this phonon dispersion structure, dispersion has been calculated in generally 0 Kelvin by DFT calculation. It shows instability due to this optical phonon. So there is a instability, and this instability actually is due to basically the ferroelectric instability. And this, as you know, many of you know, this ferroelectric is a field of soft optical phonons. Okay, so that time we thought, okay, can we combine these thermoelectrics and ferroelectrics? So because we wanted to invoke this ferroelectric instability in the thermoelectric material, but not fully ferroelectric, because fully ferroelectric it will be insulator. We don't want an insulator, so we wanted to create a local ferroelectric instability to decrease the thermal conductivity. Then this instability is basically in this tin telluride is due to basically this tin actually distort and form low temperature rhomboidal structure. So this is a paper from Japan in 1975, who experimentally observed basically below 100 Kelvin there is a non-centrosymmetric phase of tin telluride, and below above 100 Kelvin there is a cubic rock sulfate, which all we know. So now the question is that for thermoelectric, this ferroelectric instability has to come to room temperature, right? Near to room temperature at least. So in order to do that, we purposefully dope germanium in this. Okay, and you can see the DSC curve, the ferroelectric transition is coming near to the room temperature. So what is the logic behind choosing germanium? Because germanium just sit above the tin, and germanium has 4s2 lone pair, tin has 5s2 lone pair. So this as the germanium sits just above the tin, the lone pair is much more active. So germanium always try to distort the structure. So as soon as we dope germanium in tin telluride, this local we predicted local distortion in the structure. Okay. So now, basically, and then our collaborator, Professor Umesh Bhagmone, calculated the ferroelectric instability, that is the phonon dispersion. You see how much is the instability now? Huge instability. Now, if we Fourier transform it and basically see in the real space, basically we see chain-like local off-centering of germanium. And if we visualize this eigenvector, so this is basically germanium atom. This germanium atom vibrates. Okay, germanium atom, you see the distortion in germanium atom. So now that's what we predicted. But the thing is that so this is a local distortion. Okay, so what do you mean by local distortion? Because the global structure at room temperature is still cubic, still rock salt structure, but locally the germanium are distorted in a chain fashion, which is not able to capture by normal powder X-ray diffraction or crystallography. Okay, so how to see that by experimental technique? The germanium is local distorted in a global cubic structure. So this is a problem of local versus global structure in solid state chemistry or physics. Okay, so now in order to do that, first of all we have to understand. We have to observe these optical phonon modes, soft optical phonon modes, which actually coming from the ferroelectric instability. And we have done again Raman spectroscopy, and this Raman spectroscopy, this 30% sample clearly shows this low energy mode, emergence of these low energy modes, and that are basically these ferroelectric soft modes. So now how to observe this local distortion ferroelectric, which creates actually ferroelectric instability. So this slide is for students. So basically we have to do a very, very careful X-ray diffraction experiment, or X-ray. I'll rather say X-ray diffraction experiment. I'll tell you in a minute what actually we wanted to do. So now this is scattering vector. So a scattering vector is basically Q equal to 4 pi sin theta by lambda. So Q equal to, I'll write down. I forgot to write down. I'll write down myself. 4 pi sin theta by lambda. So this is a scattering vector Q, which relates to the lambda. So now for low Q, we know small angle X-ray scattering. So now, for example, if we have some, for example, for gold nanoparticle, this is a simple system. How these two gold nanoparticles talk each other, it can be determined by small angle scattering. So in low Q, if we Fourier transform, we go to the macromolecular unit, which is how two nanoparticles talk each other. So now in the powder X-ray diffraction, which is in the medium Q range, if we Fourier transform, we get lattice planes. So that means how lattice planes are there. For example, in a gold nanoparticle. Now in the high Q data, that is called a local structure region. If you Fourier transform, basically we go to the atom distances. So basically we go to the, say, for example, I'm giving an example. Just don't take it very seriously. It's gold distances. So basically we are going to nanoparticle distances by low angle, medium range. You can going basically what we do generally in lab, lattice plane distances, and from there actually in the high Q data. We can, if we Fourier transform, we get gold distances. So basically, we are going to the local structure. So that is our goal: how to see this basically this germanium and tellurium distances or 10 tellurium distances. That is our goal. So this X-ray data has been taken generally in synchrotron, because this is the small angle region, this is the powder X-ray diffraction region, and this is the flat region, as you see. This is the PDF region. This is this region. Okay. So if we Fourier transform it, we see the ripples, and you have to take this data in synchrotron sources, because you need a very high energy and high resolution data. Only if you Fourier transform, you see the important ripples, and this first peak is basically first nearest neighbor distance. That is the tin tellurium and germanium telluride distance, and the second one is second nearest neighbor distance, and third one is the third nearest neighbor distance. And my student Moinak is expert about this. And if you feed this experimental data with crystallographic model, actually you can understand this local structure. You can see first one or two peak tell you about the local structure, and wherever this range will tell you about the global structure. This is in R, because we have Fourier transform the data. So this tell about the average structure. You see that average structure is fitted very well with rock salt model, which is tin telluride structure. But global structure is not fitted very well. Okay, so in order to do that, what we have done, you can see this R value for the first peak for cubic is not at all good, or whereas the global structure fitted well with the cubic. But now if I distort the germanium around 1.1 strong, the first peak fitted very well. But the global structure is not fitted. So what we get the message from this data? The physical meaning is that the local structure, the germanium is distorted because of the 4s2 lone pair of the germanium, whereas the global structure remains cubic. Okay, and then we have done temperature dependent PDF, and we show that at room temperature, germanium is 0.1 angstrom distorted, and even above the room temperature, actually 2 TC, germanium is distorted in 111 direction, and that gives rise to local ferroelectric instability, and this ferroelectric instability actually giving the optical phonon energy down to near to the acoustic phonon, and optical acoustic hybridization happens, and we see extremely low thermal conductivity in germanium doped tin telluride, and which is one of the lowest value observed by this intrinsic technique. Okay, so now, as some of you know this field of ferroelectricity, so basically this at the near the ferroelectric transition, when this paraelectric to ferroelectric phase transition happens, this dielectric constant picks up. Okay, and this dielectric constant actually screens the charge carrier. So if we have this ferroelectric instability, we will have the screening by dielectric screening, and we will have high mobility. Okay, so you see the mobility values in these samples. So these are quite good, right? And this is actually, so we are keeping the mobility high, high at the same time we are decreasing the thermal conductivity, and that was one of the grand challenge of the field, as I told you at the beginning of the talk during the introduction part. So that means by combining these two field, like this ferroelectric instability, please don't mistake it as a ferroelectricity. This is a local ferroelectric instability with thermoelectrics, and which gives rise to ultra high ZT in tin telluride around 1.6. So this is close to this ZT of lead telluride right now. But this we make actually tin telluride is a good thermoelectric material, and this work has been done by Anonna Bonik, who is now postdoc in Gießen in Germany. Okay, so now, so I have a few more minutes, so I think I'll move on. So basically, so I'll show some of the example working in this tin chalcogenide family. So tin selenide actually, although this tin telluride, please remember, I'll go back to the structure to simplify. The tin telluride is a rock salt cubic structure, okay? Whereas tin selenide, okay, this tin selenide is a layered structure. And this tin selenide, actually the single crystal, this is such a nice single crystal made by my friend from Beijing. And then two important papers came, one in Nature in 2014 and Science in 2018. He showed that this tin selenide is an extremely good thermoelectric material which shows a ZT of around 2.6 to 2.8. But please remember, he showed this thing in single crystal. Okay, but this single crystal actually cannot be used for practical applications. So we have to have bulk scale polycrystalline or nanocrystalline sample at each level. But the fundamental chemistry and physics is extremely important in this tin selenide because it has significant amount of anharmonicity due to this 2D layered structure. Anharmonicity meaning so the phonon automatically dies down. Okay, so that means this tin selenide is extremely important material and created sensation in the field of thermoelectrics. But there was no report for this nanocrystalline material of tin selenide. So we have actually first time synthesized this germanium to tin selenide by solvothermal technique. But the trick for this synthesis is basically we have to have 2:1, tin 2 plus and selenium, because tin 2 plus actually work here as reducing agent as well as reactant. Okay, so that is the trick. Actually, many people are missing that trick and they are getting impurity. And we could scale up this material up to 10 gram in our lab. And these are in the form of 2D thin nanoplate, which are actually single crystalline nanoplate, and which shows the ZT for nanocrystalline material for the first time around 2. And this is actually third generation material, which is lead free and tellurium free and created from India. Okay, so with this tin telluride, I'll go to this germanium selenide, which is having exactly similar structure of tin selenide on the orthorhombic layered structure. Okay, the space group is orthorhombic, but it's 2D layered structure. And this paper came from Chicago by Ulverton group, who showed this computational prediction of high thermoelectric performance in GESE, and he predicted around 2.5. So this is a theoretical or computational prediction. So we got interested because we are working in tin selenide, tin telluride. So we thought, okay, we wanted to explore this germanium selenide. Then surprise is that this germanium selenide has extremely low carrier concentration, relatively high band gap. Because as we told in the introduction section, basically this you need to have band gap of this heavy metal based chalcogenides in the range of generally below 0.5 electron volt. So this has extremely low mobility, and we got ZT of 0.02, and the predicted value is 2.5. So there is a huge difference by computational prediction and experiment. But we wanted to work more. So in order to do that, we thought, okay, can we decrease the band gap? Okay, so how to decrease the band gap? So basically, we played with this term called chemical pressure. So we created chemical pressure by this alloying with AgBi-Ac2. So basically, we have made orthorhombic GESE to rhombohedral phase of GESE, which shows the band gap below 0.5 electron volt, and later it went to cubic phase. And we first time actually created this kind of phase diagram where orthorhombic GESE can be converted to rhombohedral or to the cubic by alloying with AgBi-Ac2, and these are the accelerated I can see, PNMA, then R3M, and then FM3 bar. So this was a fundamental study which actually showed phase diagram of GESE, AgBi-Ac2. But please note, this is a R3M phase and this is a non-centrosymmetric phase. So we bring this GESE in our code now. So that means we wanted to play with this ferroelectric instability. Okay, so we synthesize single crystal because we have also Bridgman growth technique in our lab, single crystal of GESE. And we have measured carefully this thermoelectric property by cutting the crystal in different directions, because once you have an isotropic structure or single crystal, people has to measure electrical transport and thermal transport in the same direction. Please note, we have to measure in same direction because many people does mistake while doing measurement for the single crystal. So we cut in different direction and measured same direction electrical and thermal transport. And this 10% AgBi-Ac2 GESE sample is rhomboidal, and you see the electrical conductivity is now high. and the mobility value suddenly increases. Okay. So this mobility value increases because it is first of all single crystal, and it has basically the dielectric charge carrier screening because this ferroelectric instability, because this is a non-centrosymmetric phase, and Umesh has calculated basically this electronic structure which shows multiple values. Because I have not much time to talk about this electronic structure modulation. This is equally important and interesting as I am talking about this thermal transport, because when you have these multiple values, basically the charge carriers are basically in the case holes are distributed in different values. So it can move in different path, and we will have high mobility in this system. And then see the thermal conductivity. This is the lattice thermal conductivity. This is orthorhombic phase, which is nothing to do with ferroelectric instability. As soon as it becomes rhombohedral, the thermal conductivity actually decreases near to this theoretical minima, and this actually happens because of this local ferroelectric instability in this system. And we have generalized the concept of this introducing ferroelectric instability in this thermoelectric field in this material, and then to show directly this ferroelectric instability. First, this is not a direct proof, but this is again a prediction. So we have collaborated with Umesh, and Umesh shows this low energy optical phonon modes in this rhomboidal phases, and which is below 50 centimeter inverse, and that is because of coming mostly from Bismuth, germanium, and many others. So don't bother about this thing. Now we'll go to the experimental proof. Again, we have done low temperature heat capacity measurement, which cannot be fitted by DAY model. We have to invoke this Einstein term, and this Einstein term again I am telling you this low energy optical phonon modes, which are coming due to this ferroelectric instability in this material, and which gives rise to optical acoustic coupling. So the direct proof is basically if we can observe this ferroelectric domain, and Gautam Seeth, Professor Gautam Seeth from ISR Mohali, he has this piezo response force microscopy, and he is basically one of the very good friend of mine, and also one of the famous condensed physicists. So he showed basically there are ferroelectric domains in PFM, but the opposite color, different color domains, basically different contrast domains tells you the different direction orientation of the domain. And we see the hysteresis and butterfly loop, which is the hallmark of ferroelectric instability in this material. And we have together published many important papers in this area. We have no time to show all this, but we have shown basically by introducing ferroelectric instability, we can generate low thermal conductivity, at the same time high carrier mobility, and we can get a ZT of 1.2 in the single crystal of germanium selenide, which was predicted to be good thermoelectric material by calculation, but later it shows orthorhombic phase is not a good thermoelectric material, but you have to go to basically this rhomboidal phase. Okay. So now, how many minutes I have now? How much time I can talk?
Sir, you have half an hour, 30 minutes.
Okay, so what I'll do, I'll just finish it 5-10 minutes, and then I'll take love to have some questions. Okay. Okay. So another important sensation in the condensed matter physics and solid state chemistry is basically topological quantum material. Okay. So this is a bit complex field, but I'll try to simplify as much as I can. So this topological quantum material or topological insulators are having the surface states which are metallic, but this has a band gap, like insulator or semiconductor. Okay. But it has surface states, and these surface states are protected by different symmetries. For example, if I have strong topological insulator, which is bismuth selenide Di2Ac3, which is a very well-known material. It has metallic surface states which are protected by time reversal symmetry. But there are topological quantum material called weak topological insulator. So these are formed by the heterostructure of 2D topological material. And this weak the name weak is given because this kind of heterostructure has surface state not in all the direction. Okay, so it has surface state in certain direction, and which is again protected by time reversal symmetry. But it has even number of Dirac cone in the side surfaces. But in the strong topological insulator, it is the odd number of Dirac cone. Okay, so to simplify, what is strong and weak topological insulator? Strong topological insulator are well known. These are all generally 2D materials, and this has all the direction surface states. But in a strong, weak topological insulator, these materials are generally heterostructure of 2D strong Ti, but they don't have surface states in all the directions. They have selected direction surface states. Okay. So now, we have discovered basically a homologous series called Bi2M, Bi2Ac3N. As you know, this material is well known, which is a strong Ti. So now, once you create this homologous series, basically this homologous series actually is a compound generating machine in solid state chemistry. So how we can generate new compounds? For example, if I have M equal to 0, N equal to 1, this is bismuth selenide. Okay, but when we have M equal to 1 and N equal to 2, so we have M equal to 1 means Bi2, and here also N equal to 2 means we have 6 total Bi and Ac6. So basically this is called simply BIAC. So BIAC is a new member of this family, and there are other members we have also published in different journal on this study. But to simplify, BIAC has similar structure to Bi2Ac3, but in this van der Waals gap, we have a bismuth bilayer. Okay, so this is the bismuth bilayer, and because of this bismuth bilayer, this becomes a weak topological insulator, and this is well proven in the literature because this has a heterostructure, natural heterostructure type nature. So we studied thermal conductivity of this compound, and surprisingly, the strong Ti has a reasonably good thermal conductivity, but weak Ti has ultra low thermal conductivity. So what is the reason for that? So the main reason actually, again we have done low temperature in order to understand what is the reason for having low thermal conductivity in weak Ti. Basically we again fitted this low temperature heat capacity by Debye-Einstein model, and which shows low energy optical phonon modes. So all my work today I'm going to presenting everywhere we are seeing low energy optical phonon modes. Because why we are doing this? Because optical phonon energy actually we wanted to equate to the acoustic phonon energy so that it can scatter each other. So basically scatter the acoustic phonons. That is the idea. So basically we are creating soft modes in this material, and this soft modes has been proven by phonon dispersion calculation by Umesh, which shows this low energy optical phonon modes from the purple atom, and purple atom is actually from the bilayer. Okay, you can see this is atom projected phonon dispersion curve, whereas Bi2Ac3 the optical phonon modes actually this is coming from bismuth from this layer, quintuple layer. So bismuth in this layer is also bismuth is there. So the bismuth selenide having optical phonon modes from this layer, but low energy optical phonon modes, and BIAC is coming from this bismuth bilayer, and this bismuth bilayer actually vibrates. They localize vibration, shear type vibration or different type of vibration, and which creates this optical acoustic coupling. So this is basically avoided crossing, which is hallmark of this optical acoustic coupling, which actually give rise to ultra low thermal conductivity. And please note this is the N-type material, because N-type material is extremely layered in thermoelectric, and this is the ZT is near room temperature. So this is basically near room temperature power generation, or this can be used for basically Peltier cooler application also. So this material has significant applications. We have filed a patent also. So to move on, so the last example I'm going to give you this perovskite halide, because perovskite halides are sensation in solar cells right now. So all of you know this, I think, about the solar cell. I'm sure there will be talk in solar cell. Already there are talks in this school. So now we are interested in perovskite halide as well in our group. So now we are mostly interested in complex layered two-dimensional perovskite. So this is called Rudensson-Popper phase, which is CH2Pb2I2Cl2. So we have grown the single crystal, and this is the structure, and this structure can be visualized as perovskite type of layer and rock salt type of layer. So this is a bit complex, but this Rudensson-Popper series is well known for oxides, and which are well known for superconductivity. Okay, so these structures are also well known, but this kind of structure is very new to these halides, perovskite halides. So we have made the single crystal by Weismann technique, and we measured the thermal transport property in different direction. So this thermal transport property, what is the data? Okay, I forgot to put this data of thermal transport. Yeah, so this thermal transport data, basically it shows ultra low thermal conductivity. So we bring this perovskite halide in the field of thermoelectrics for the first time, which shows this ultra low thermal conductivity without doing mesostructuring or grain boundary engineering or point defect. So this is again an intrinsic effect, and this thermal transport is extremely important in solar cell, as I mentioned in the introduction, because this there are phonon bottlenecks which creates problem in solar cells. So this field also demand low thermal conductive material. So this low thermal conductive material not only important for thermoelectrics, it also important for solar cells or optoelectronics. So now we have to understand why this perovskite halide shows this ultra low thermal conductivity. So in order to do that, we have done analysis of this bonding, and you can see where Pb and iodine bonding, the force constant is extremely high. So that means this is a covalent bonding. From the chemical intuition also we can tell. Whereas this cesium, which sits here, does not interact covalently. So this has ionic bonding. As I told you, we are fond of chemical bonding. So we actually created again bonding hierarchy in this material, and this bonding hierarchy actually give rise to low energy optical phonon modes. And you can see this low energy optical phonon modes, and even this chlorine modes comes down to below acoustic phonon modes here in X2Y point, and there is a significant coupling between optical and acoustic phonon in this material, and which gives rise to very low energy modes like 12 centimeter inverse and 25 centimeter inverse. 12 centimeter inverse is due to this dynamic rotation of this octahedra, which is coming to this 3s2 lone pair of chlorine, whereas this 25 centimeter inverse modes basically the shear wave between the layer, and which altogether give rise to this low energy optical modes in this material, which is again determined by this Raman spectroscopy. But the phonon light time we have calculated from the FWHM, that is full width half maximum from this Raman data, is around in the 0.5 to 4 picoseconds. So this phonon dies very fast in this material. That's why we see ultra low thermal conductivity due to this dynamic rotation and dynamic tilting of the octahedral, also the bonding hierarchy. So with this, I'm going to conclude now. Basically, before concluding, I'm going to show like what is the progress for high ZT material and devices from our group. Because this not only fundamental problem solving, the material should go to the industry, and material should go to the market in this field to have bigger impact. So if you see for near room temperature, materials are generally discovered and based on bismuth telluride are from South Korea, Boston and Houston, both are from US. Whereas this high temperature material is discovered from Chicago and Beijing, and some of the material from JNC, but in mid temperature range, we have generally discovered most of the material which is generally based on germanium telluride. I didn't talk about much about germanium telluride today. And we have actually made device in our lab. We have a device, thermoelectric device lab. We show single leg ultra high efficiency of around 12%. And with seeing the progress, actually Tata Steel contacted us. Because as you know, this Tata Steel has steel, makes steel, right? This is very famous worldwide. And then they have blast furnaces, and they actually have huge amount of waste heat in this Tata Steel power plants. But what they want from us right now, they want recovery of low grade waste heat, because this is a real picture of this Tata Steel plant I have taken when I visited. So this Tata Steel plant, you can see this many pipes actually run throughout the plant. So that means they cool these blast furnaces by water, basically steam. So that temperature of the steam is around 115 to 110 degrees centigrade, and they want to put thermoelectric devices in these pipes. So basically they want material in the 400 to 450K range. So actually we are actually working together for last 1 year with Tata Steel to develop new N and P type material. That's why this BIC is extremely important. So and we have a tripartite collaboration where we make device together and try to put prototype in this pipes, and hopefully it will work in steel power plant. And with that, I'll try to conclude. So today I talked about majorly fundamental issues in thermoelectric related to the phonon transport and thermal conductivity. So intrinsically low thermal conductivity is an attractive paradigm for developing high performance thermoelectric material. So today I showed how bonding hierarchy, creation of bonding hierarchy is important, where coexistence of rigid covalent substructure with weaker substructure is important, where we can get phonon glass electron crystal type behavior. So engineering ferroelectric instability is one of the key, and this is came from our lab, this concept in thermoelectric field. And how we can choose a new thermoelectric material, where you have to you see this large atomic ADP means atomic displacement parameter or strain lone pair. Actually, if you see the crystallographic data for the heavy metal based chalcogenide or other material, I think you should measure the thermal conductivity. But fundamental understanding of the chemical bonding and the crystal structure, basically local versus global structure, and its correlation with thermal transport are the key. So acknowledgement. So we have a very good PhD student, master student, as well as postdocs in our group, and they generate a lot of new ideas. And then we work together, and then I have excellent collaborators starting from Umesh Wagmare, Shapon Pati, Sorita Gasti, Gautam Sid, Ditya Sanal, Pankaj Mondal, Abhishek Singh, Ajay Soni, Sobhit Bhattacharya, and then Supriyo Sarkar and Neha from Tata Steel. And I have generous funding from ACRB, DST, especially throughout my independent career. Recently from Tata Steel, also we have a fund from Shikshaka Laboratory in JNCSR and my startup grant from New Chemistry Unit in JNCSR. So I will be happy to answer all the questions if you have. Thank you very much.
Thank you, sir. Thank you very much for a nice informative talk. So now this talk is open for discussion. I request the participants who join on this Microsoft team, you can please raise your hand to ask the question.
Professor Viswas?
Yes.
You have shown the pair distribution function where it goes to negative. Can you explain me why it is going to negative around 31 or 32?
No, see.
Slide.
Yeah, so this
slide
negative,
31 and 32.
Yeah, I understand. So this pair distribution function generally goes to negative. So this is not an artifact. So basically, see this is GR. So GR is a radial.
Yes, yeah.
Okay.
Because
so it goes to negative.
Yeah.
See, it's related to basically the statistical mechanics. So I am sure that all of you know, or at least some of you know, what is the radial distribution function in liquid or something. So this is a radial distribution function or paired distribution function in solid. If you see a radial distribution curve, and in your statistical mechanics book, it goes also to negative. It's not a problem.
Sir, actually, the paired distribution function, it describes the probability of finding two atoms which are separated by a certain distance. So it's a probability. Yeah. So the negative, it doesn't make sense. Like it should not be negative. It's always the probability. It is always positive.
Yeah, it's generally positive in radial distribution function, but this is a Fourier transform data from a real experimental data. So this is a well practice in this field to have data from 0 to above 0, which is basically positive probability, and also negative. And these are not the peak; these are the deep basically. So this is coming from the real data, and which is real like general practice in this field in paired distribution function.
Okay. And when you calculate the total thermal conductivity, so you take a different scattering mechanism.
Sorry?
So scattering mechanism, the scattering mechanism, thermal conductivity, in a Boltzmann transport equation or any theoretical explanation. So what are the different?
I have not shown. Sorry, I have not shown any Boltzmann transport equation.
No. You have shown if there is a defect scattering. What are the in theoretical simulation of experimental thermal conductivity, lattice thermal conductivity calculation. Yeah. So one has to take into account the different relaxation processes.
Exactly.
Scattering processes. Yeah. Okay. So so what are the, as you said, the Grunstein parameter like anharmonicity you take into consideration. So apart from that, what all other scattering processes you have included? Like, did you
actually, I have not done the calculation of thermal conductivity. First of all, you have to understand when you have experimental lattice thermal conductivity, why you need theoretical lattice thermal conductivity. So this is real experiment. So I have shown basically Grunstein parameter to show the anharmonicity. But I understand your question. One can match the theoretical modeling of thermal conductivity by Boltzmann transport, but we are not interested in that because we are doing real experiment. Okay. So, but one can do that. One can match with the experimental data to understand more about this scattering, basically these taus. You are asking about the taus.
That exactly, okay. Taus.
So generally, it can be done and then it can be shown in the point defect rich sample. You can include tau for point defect, you can include for particle, you can include for grain boundary. That there are different taus. So there are several theoretical groups working in this field, but our group is an experimental group because once you have experimental data and TEM to show nanoprecipitates and you know the structure very well, you don't need to have support from theoretical thermal conductivity. Because if you are predicting a new material, which is not done by experiment, you can do all this tau calculation and tell that experiment is to make the material and show that thermal conductivity is this much.
Okay, sir. Okay.
Yeah.
Okay, thank you, Professor.
Yeah, thank you very much.
Nice.
Thank you for asking this
Well,
question. Yeah.
Vishwas, I want to continue on this the same question because here you have shown this thermal conductivity of lattice.
Yeah.
So how do you extract it? Because in thermal conductivity, you will have the contribution from electronic part as well as lattice part.
Okay. So what you are talking, basically, this is the part I told in my introduction. So this is basically, if I am writing the equation, you can see this is the lattice part, right? This I'm extracting from here. So now, as you know, this part is equal to L sigma T. Okay. And this part we directly measure by laser flash technique, which is a well-known technique in the field. So now we measure separately this electrical conductivity of the same piece. So then we can calculate this K electrical part, and you minus it, you get basically this K lattice part. Okay.
Okay, thank you very much. Thank you. Thank you.
So this is basically famous Weidemann-Spann's law in solid state.
Yeah, but measuring thermal conductivity is not an easy task. So it's very nice. That's why if I want to make the setup for thermal conductivity, it is really tricky to measure it.
Exactly. So basically, we have very good setup to measure thermal conductivity, and this is one of the state-of-art facility, and it's there actually. It's compared to the world facility we have in the state-of-art thermal conductivity measurement.
Vishwas, I want to ask one question. Maybe
Sure.
that will, see, you mentioned that the ferroelectric instability in this thermoelectric, and I have read your that very nice paper with Gautam Singh.
Yeah.
So my question is, so should we assume that these non-centrosymmetric materials are good having less thermal conductivity? Can we make this generalized statement?
Yeah, it's a very good question. It's a very good question. So we have shown few of them. Of course, this ferroelectric instability in non-centrous, if you have an intrinsic ferroelectric instability, it shows so low thermal conductivity. As you know, if you measure, because I don't have the data for germanium telluride. You know about germanium telluride. So this is one of the simplest ferroelectric material, right? So a lot of work has been happened in terms of ferroelectricity in this material. And this is also another good thermoelectric material. And this, if I plot thermal conductivity versus K lattice versus T of this material, so this material thermal conductivity starts from 3 watt per meter Kelvin. I'm not writing the unit. It shows goes and dip and then goes up. Okay, and this dip actually basically this paraelectric to ferroelectric phase transition of this germanium telluride. Okay, so this lot of work happened in this material, but this more work has to be done because what we are talking. Bringing this ferroelectric instability to decrease this low energy optical phonon modes, these are the new concept in this field. So it has to be cross-checked in many non-centrosymmetric material. And of course, this material is also non-centrosymmetric.
Thank you very much.
Yeah.
So Rajesh, do you have any question from the YouTube? I can find
yes,
one.
Sir, we have a question from an attendee, Nihal Limbu.
Hello.
Yes,
sir.
Yes. Nihal, can you can ask your question? Yes, please.
Hello, sir. Good morning, sir.
Yeah.
My question is how to make the junction in Peltier module?
Sorry?
Sir, how to make the junction in Peltier module? In thermoelectric cooler, how to make the junction? You made it now?
Okay. So let me simplify your question and tell to everybody what he is asking. So what is your name?
Smritiranjan Senapati.
Okay, so what Senapati is asking basically how to make junction in Peltier cooler. So this is more like a engineering question. Okay, engineering task. So what he is asking, I go to the device. So let me understand. I am correctly understanding this your question or not. So what you are asking basically?
Sir, I am a BTech 4th year student.
No, I got it. I got it. Your question. So you are telling how to make this junction, right? This junction. Okay.
Yes, sir.
So this is more like a device engineering question. So what today I talked about this materials aspect, this part. But we do this making this junction, which is a real difficult task because you know. So this contact resistance actually deteriorate this thermoelectric efficiency of a device. So in order to do that, generally what people do, so they make this material, they make a powder, and they consolidate this powder in spark plasma sintering. Okay, while consolidating. So for example, this is PBT. This is a standard material,
yes,
and
sir.
they put some iron. Okay, and here also some iron and also tin, and then all this powder they consolidate in SPS and then they make this lake. and then they connect this basically this bridging material with another N-type material by copper strip. Okay, and this copper strip a little tricky to add this copper strip, and this is a copper, and you have iron ore tin, and then you have this thermoelectric material, and similar way you have this copper strip here. So generally this process has been done like this by spark plasma sintering.
So that means we have to make it by bridging process.
Exactly.
Okay, thank you, sir. Thank you so much.
Yeah.
Thank you, Senapati. Now I request Nehal. Please ask your question.
Hello, sir.
Yeah.
Sir, scudderite compound is also considered one of the best thermoelectric material.
Right.
So why you have not chosen that material yet to study the thermoelectrics?
See, we in our group we work on new material generally, and then our expertise or our interest to study these chalcogenide, that means selenite, telluride, sulfide. And scutterolide is of course a good material. This is basically scutterolide. You can see, I'll write down the formula. Let me get a open space. So scutterolide, for everybody I'm writing this. So scutterolide is formula is COSB3, right?
Yes, sir.
And then the COSB3 has void. Okay. And then COSB3 has void, and you put gas rattler like say terbium, dysprosium, all these heavy elements, right?
Yes.
And this rattles in this channel of the scutterolides and gives rise to low energy optical phonon modes.
Yes,
That is also known in scutterolide, but you are having a gas rattler here. From a chemist point of view, you don't want to add any foreign element. So what we have done in thallium selenide, you can see here why we are actually different from the scutterolide. What is that thallium selenide? So thallium selenide, okay, 1 minute. Yeah. So this thallium selenide, this is the rattler, which is thallium plus one, which is there itself in the solid. So this is the intrinsic rattler, whereas in scutterolide field, generally people choose extrinsic rattler. So that is the difference. And of course, scutterolide, lot of work happen, and somebody can do a scutterolide, but we are not interested really in intermetallic thermoelectric at this moment.
So actually, I'm doing on that only. I'm doing theoretical research on that thermoelectric.
Yeah, because scutterolide ZT, you can see also in terms of ZT, scutterolide maximum ZT I have seen paper in JAX from Li Dongchen group is 1.6. Okay, from Shanghai. But if you see the telluride exceeded 2.2 now 2.5 also. So that's why we are more interested in tellurides right now.
Okay. Sir, and one more question. I find that more the structure is complex, the lower the lattice thermal conductivity.
Exactly.
So could you please explain or elaborate how it actually happens?
So as you work in this field, I think you are asking really important question to the field. So once you have complex structure, so this is also complex structure. So complex structure, you have lot of atom in the unit cell. Okay. So once you have lot of atom in the unit cell, automatically that phonon dies down. Okay. So then you have low thermal conductivity from the complex structure. So there is a nice review by Jeff Snyder from Caltech and Northwestern in Nature Material. The title of the paper is basically complex structure for thermoelectricity. You should read that. Okay. So this is one of the aspects from phonon transport. But if you think once you have a complex structure, you have multiple electronic valleys in valence band and conduction band. So once you have multiple valleys, basically you can channelize the carrier in different path. So you can have high mobility, and because of this multiple degeneracy factor, you have high Seebeck coefficient. So there are multiple effects of this complex structure.
Okay. Sir, and one last question. Sir, in slide 19, I see some of the phonon modes are negative.
Okay, very good question.
So, and now I find that phonon, that means when the modes are negative, it's dynamically unstable.
Exactly.
So how can one further investigate if the material is unstable? And how does it affect?
Okay, so from the theoretical point of view, you are saying at 0 GPa, this material is unstable. Okay. So now if you see the crystal structure, the material is stable, experimentally stable. Doesn't matter theoretically unstable or not. But when you have a very low energy phonon modes like this, so that means theoretically the structure is unstable, but you have to find, you should not throw that work. You should find it out which direction and which phenomena this structure is getting unstable. So what we have done, we have calculated the phonon structure at 1 GPa and try to find it out the eigenvectors. Eigenvector means which atom is responsible for these phonon modes. And then we find it out actually this thallium vibrations are actually creating this instability, and which is nothing but the rattler mode. Okay, because once we have this rattling, with thallium is moving around this channel, the structure tends to unstable, right? So that cannot be taken care by this basically phonon calculation at 0 GPa, but we have to have some strain by 1 GPa and to get this stabilized. But it has given an important information which atom is getting destabilized. Okay.
Okay. Yes.
Okay. Because you should not throw the work as soon as you get a negative phonon mode.
Okay, sir. Okay, sir. Thank you very much.
Yeah, thank you, sir, for the elaborative answer. Now I request Sneha Susan. Please ask your question.
Good morning, sir. Hello, am I audible?
Yes, you are. Please ask.
So actually my doubt is when you told about initially...
I cannot hear you. Can you please talk a little louder?
Hello, can you hear me?
Yes. Yeah.
Yeah, okay, sir. Initially, when you spoke about nano precipitates, you told that like we don't use, like we will go for because nano precipitates, when you add them, it becomes extrinsic. So we look for some intrinsic properties of material.
Right.
Later on, sir, when you spoke about germanium substitution in selenium telluride, I'm sorry, tin telluride,
Yeah.
At that time, sir, isn't that also extrinsic? Like when you add germanium.
Oh, okay. I got your question. It's a very good question. Okay. It's a very, very good question. What you are talking, basically, this slide. Okay.
Yes, sir, this slide.
Oh, no. Okay, just a moment. I'll come to that slide. I understand. Very good question. Yeah. Okay, so you are talking that we are substituting germanium. Okay, so basically you are talking this germanium we are substituting. So this effect may come from point defect scattering, right?
Okay, sir.
Right. See, we are creating point defect as well, right?
Yes, sir. Yes, sir.
Okay, but we have done TEM. There is no nanoprecipitate in this sample. First of all.
I know. Yes, sir. That's what. So.
Okay. So now there is a model called Clemens model. So you can actually model this thermal conductivity, as one of the faculty members was asking that question. So basically this point defect actually can decrease the thermal conductivity from here to here maximum. Okay.
Okay.
Not here. So there is an intrinsic effect here. And this intrinsic effect is coming from the ferrolytic instability. I'll go back to this lead telluride slide.
Okay.
Because we have nullified, there is no nanoprecipitate. Now you see this. Okay, what is that? Okay, 1 minute. Yeah. So this is the point defect. You see how much it is coming for lead telluride. Okay.
Yes,
so this effect is coming due to the nanoprecipitate. But if you nullify the nanoprecipitate in tin telluride, basically this effect, which is seen in tin telluride, is actually due to this ferrolytic instability that we have done very, very careful study to show that there is no nanoprecipitate.
Yes, sir. Okay, sir. Thank you very much, sir.
Yeah.
Thank you, sir.
Thank you, sir. Now allow me to ask one or two questions from the YouTube.
Sure.
Thank you. So there is one question. Is there any toxic effect due to the presence of PD in your material?
Not PD, lead.
Lead,
PD is palladium.
It should be PB. Yeah, palladium. Yeah.
Okay. So see, of course, lead is toxic. But can I ask you a question? Do you run a car?
Yes.
Hello?
Yes.
So what battery you use in your car?
No, I am just asking the question on the behalf.
No, I'm just giving the answer. I'm just framing the answer. So what battery you use in your car?
Battery, okay, lithium, I guess.
No,
I don't know.
Not lithium, lead acid battery you use.
Yeah, lead acid, sorry, yes.
Okay. So that means these car companies are having this lead acid battery for years after years, right? Exide and Amaran, all these battery companies. So that means if you can seal properly, and these are all solid state material, even lead acid battery has solution, right? So there is much more risk. But if you have lead telluride, and lead telluride thermoelectric generators are in the market, but these are all solid state material because you have lead poisoning only if the lead is in the solution. But of course, in our group, we wanted to make lead-free material, as I told you in throughout my talk, and I have not given any example based on lead, but I back this lead telluride in this field equally, because lead telluride, if it is sealed properly, it should not have a problem because this is in solid state. Okay.
Okay, sir. So there is another question. Pardon me for the pronunciation. Scurrodides PGEC are considered to be one of the best thermoelectric material.
Yeah.
Why you have not chosen such material yet?
So already I answered this question. I think somebody asked COSB3, that is the scutterodite. And this PEGC concept has only showed ZT of 1.7, but it didn't able to show ZT above 2. So, and this scutterodite is an extrinsic rattler, and we have the material which is intrinsic rattler, and some of the material what we have showing ZT above 2. Hello, do you have any more questions?
Yes, sir. I have one more question. What are the material used in increasing efficiency of solar PV panels?
No, see, sorry.
What are the materials? Am I audible, sir?
Yeah. Please go ahead.
Yes. What are the materials used in increasing efficiency of solar PV panels?
Okay. So basically in solar PV, you cannot add material in solar cells. What you have to have. So generally, basically you have solar cells, right? All of us have seen solar cells. It's everywhere almost now. So solar part has light and heat. So this heat part can be captured by thermoelectric generator once you install thermoelectric generator down the solar panel. Okay. So you don't have to modify solar panel. So, and then basically this heat part can be converted by thermoelectric, which is down the solar panel, and solar part can be converted light to electricity, and both the electricity should go to the same place. So that some don't have to modify the solar cell, but you can separately use in a parallel circuit this thermoelectric generator just down the solar panel.
Okay, sir. Thank you.
Thank you very much.
Thank you, sir, once again on the behalf of Department of Physics NIT Jalandhar. We are thankful for taking out time from your busy schedule. Now I request Dr. Kiran to kindly take over the session.
Yeah, thank you very much, and I'm really enjoyed.
Thank you, Rajesh, and thank you, Professor Knishka. Thank you very much for accepting our request and deliver a very nice expert talk on thermoelectric to this audience. So I am very much thankful to you, sir, and we would like to see you in person in Department of Physics at NIT Jalandhar. So thank you, sir. Thank you again. Thank you very much, sir.
Thank you very much, Kiran, and then hope to see you soon. All okay.
Sure, sir. Sure, sir. Thanks a lot.
Shall I close now?
Yes, sir. We will close now.
Yeah.
I will just. So for the audience, please, we will meet at 3 o'clock. And don't worry about the feedback link. I will send you an email. Thank you. Thank you very much. Thank you, Viswas, again for a very nice presentation and hope to see you soon. Thank you.
Thank you, sir. Thank you. कैसे वो साहू कैसे तो निगेटिव में आगे आगे पर हटाई नहीं ओके Hi, Kiran.
Good afternoon, sir. How are you, sir?
Yeah, how are you?
Namaskar, sir.
Namaskar, namaskar.
I am fine, sir. I am fine.
Okay,
How are you,
good.
sir?
Yes, good.
Good to see you, sir.
Yes. So it's good that you are arranging a big meeting. It's good.
So thank you, sir. It is due to your cooperation, sir.
Yeah. Yes.
Thanks to all our speakers.
Oh, good.
Everyone kindly agreed to deliver the talk.
Okay.
So how are the things at your end, sir?
Yeah, things are okay. Not bad, but it's not quite normal. So
you are in Bangalore, sir, or at your home?
Yeah.
You are in Bangalore.
But at home.
Okay.
Sometime I do. Otherwise, office many people just come and disturb.
That's true.
Yeah.
Because you have to sign many things, so you have to.
Correct. I'm the chairman for that unit, and so people come and disturb.
Yeah.
So I'll go after some time. So.
Okay. I think, sir, things will get normal soon.
Yeah.
So, what about your foreign visit, foreign responsibility? So, you are visiting, or
where?
For example, you are visiting Japan or UK or not?
Nothing. Nowhere now.
Nowhere these days.
Nowhere. Yeah.
Okay, sir.
Yeah.
Sir, we will start at 3. So,
yes, I will wait.
If you want, you can share your slide just to see that whether it. I will make you a presenter first.
Okay, 1 second.
Just 1 minute. Just 1 minute, sir. I have to make you presenter.
Okay.
Just 1 minute, sir. Yes, sir. Sir, now you are presenter, so you can try.
Do you see?
Yes, sir. Everything. Just make full screen for a moment.
Correct.
Yeah, everything fine, sir.
Okay.
Yeah. So if you want, you can keep it, or you can minimize. We can have your photograph. Yeah, you can minimize for a moment.
Okay.
Or you can stop. You can stop presenting and then.
Okay. Yeah.
Again, you have to click that one, the same from where you started the presentation.
Correct. Yeah.
But you have to escape the full screen, I think, first, because you were not able to see anything.
Correct.
Yeah, now it's fine. Yes, sir. So we will wait for 4 minutes.
Okay. So what is the time, and I should stop?
Sir, it is up to you. So it is in our schedule. It is 1 hour 30 minutes.
Okay. So you will have some questions and.
Yeah, we will have questions also. So you can stop around 1:20 or.
Okay.
So that you can complete everything at 4:30. Otherwise, it will go 4:45.
Too long. Yeah.
Yeah. So you have to take care of that.
Yeah.
So I'm saying, sir, very nice work. You are doing very nice work these days.
I didn't leave it. So
it's good, sir. It's good. See,
lot of learning. learning.
Lot of learning, sir. Lot of hidden fact which were not knowing earlier.
Correct.
Of course, okay, we cannot make this application at the moment, but okay.
It's fine. So at least this itself great, because so understanding, then only we can contribute anything. So initial stage, my understanding was not, because I was coming from so different backgrounds.
That's true, sir. That's true.
And magnetism and then the symmetry aspects are very
sir,
much.
You started from superconductivity, CMR.
Correct. So and then this ferroelectric and this field is completely new. But now we are good. But now seems to be, you see a saturation. People, not many are working on this field.
Sir, I don't think in this way. I will put this question in another way. See, multiphorics let the people to understand, go to the pair distribution function, to know the interaction and know the symmetry, local symmetry, or for example, exarchs. So multiphoricity opened many new areas where people were not worried too much earlier.
There are a lot of new things emerging from this also.
Yeah. So, for example, in the morning, Biswas was showing that ferroelectric domain in this thermoelectric materials. So that is again the concept of presence of non-centrosymmetry. So by structure, it is sometimes very difficult to say that whether the crystal structure is centrosymmetric or non-centrosymmetric. So in this way, it's okay.
Yeah.
And this neutron studies magnetic structures.
Yeah, they are very much essential.
Yeah, very much essential, sir. Very much essential. And the good thing is, sir, your facility is really very good now, because the good thing is that it is not a commercial available facility, and you have developed at your end. I can understand how much time it will take.
Yeah, it's okay. Satisfaction. So at the end of the day, you feel that okay. Now we found many materials which were not known to be that way. I'm happy that
I am following your work regularly, sir.
Okay, thank you. Yeah.
After joining here, okay, little bit, I am not doing too much research because of this teaching. But okay, now I have students, so we will start. So, sir, in this short-term course, due to our expert team, we are having more than 1,080 participants.
Really?
Yeah, sir. So more than 180 participants registered for this course, and I got many requests after that.
Oh, that's great. Very big.
Not only from India, from abroad also, sir. So we are different countries, because in these days, in private university, people are from different countries, and now when they are going back, they have some network. So we have students from Spain, Canada, France. Yeah, sir. And many people from Nigeria, Philippines, Algeria, Pakistan. So a lot of people are there.
Okay.
So we have many faculty members, and they are, because this online teaching, they may not be able to join the lecture now, but they are seeing those lecture on the YouTube.
Oh, it is available on YouTube?
It is available on our website.
Okay.
So whatever we are talking, it is running at the YouTube also.
From your website?
Yes, sir, from our end.
Oh, okay.
Vedai, are you there?
Hello? Am I audible, sir?
Yeah.
Okay.
Okay, we are going to start soon. Huh?
Yes, sir. So, very good afternoon, everyone. I welcome you all on the second session of third day of short-term course on advanced energy materials.
Just a minute. Let me check whether it is available on YouTube. Wait for 1 minute.
Okay, sir. Okay.
Just wait.
Yes, sir.
Professor Sundaresan, very good afternoon to you and all the participants who are attending this course. Sir, thank you very much for accepting our request to be the part of this short-term course on advanced energy materials. So I welcome you, sir. So now I request Vedai to start the event. Vedai, please.
Thank you, sir. So once again, welcome everyone. I hope you have your lunch and ready to attend the next talk. Dear participants, the speaker of our next talk is Professor A. Sundaresan from Jawaharlal Nehru Center of Advanced Scientific Research, Bangalore. It is a great honor for me to introduce our today's guest. Dr. Sundaresan is a professor in Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. He has obtained his PhD from IIT Bombay in 1994. He worked as postdoctoral researcher at various places. Dr. Sundaresan did his postdoctoral research from CNRS lab, Crismat, France. He was an invited researcher at LEPES, CNRS, Grenoble, and researcher of CREST JST at AIST, Tsukuba, Japan, before he joined JNCASR, Bangalore. He has published around 200 research articles in different international journals. Sir has 3 patents and more than 7,000 citations. His area of interest and research are solid-state chemistry and physics, multiferroics, magnetism, and superconductivity. I extend a very warm welcome to you, sir, and I request you to please enlighten us with your talk. Sir, please.
So thank you very much, both of you, for giving me an opportunity today to speak to the gatherings. So thanks all for joining. So let me make a video to make it better and then share my content. Yes. So this workshop is on energy materials, but we are not going, this magnetoelectric or multiferroic materials, they are not producing energy, but they are conserving energy, they are saving energy. Okay, so that is the purpose, but still I will not go into fundamental application point of view because there is a long way to go. So today, since it is a kind of workshop, so I will mostly focus on the basics and then give an examples because I started this field as a newcomer into this, and then I learned along with my students. Okay, so today I am going to share with you actually my journey is last 10 years or so on this field of magnetoelectric and multiferroics. So I think it's good. It's very hard to see such kind of things because that's why I suffered a lot to understand this field. But now, at least we are comfortable to know what we are doing at least. So I'm going to tell you this. Okay, so okay, so this is going to be a very simple outline of the talk. Let me first introduce the symmetry aspect, which is very important for the magnetoelectric and multiferroics. Okay, otherwise, if we pick up a wrong thing, wrong symmetry, a material with wrong symmetry and claim to be magnetoelectric or multiferroics, and this can be a wrong thing, a wrong result as well. So symmetry, understanding the symmetry is very important. And, both chemists and physicists, they study crystallography, to understand the symmetry, but not many people study the magnetic symmetry, okay, but which are very important here to understand the magnetoelectric effect which particular linear metallic effect and multiferroics. So when we say multiferroics, the word very general, what it means is you are combining at least two ferroic properties. One is the ferroelectric property, what is shown on the left hand side, P versus E gives you a hysteresis, and the example, well-known example is barium titanate. Okay, this most importantly the TiO6 octahedra. What is shown here in the one state, the titanium is moved along the one of these oxygen octahedra, okay, in the tetragonal structure. But when you reverse the pulling electric field, it's just the opposite side. So you see a switching of this. So you have the hysteresis. We know all this about the what is ferroelectricity, and this is typical curve of PE loop in a very good system like barium titanate or PZT. So on the right hand side, you see, so most of these classical, the ferroelectric materials like barium titanate, okay, all these things has D0 electrons, so no D electrons. That's a very important requirement for this, because of this requirement of equivalency or second order Iontaylor effect, which comes into play when we need to have this ferroelectricity in this material. And on the other hand, magnetic material, when we say magnetism means ferromagnetism, that's very obvious to say, or ferrimagnetism. And a simple, maybe an example is doped manganite. And that also you can see a hysteresis similar to ferroelectric hysteresis, where you have M versus H instead of P versus E, where you increase the field and then you reverse it, you get a hysteresis. That also we know. This hysteresis is typical of ferromagnetic, okay, and you have the 1 and 0 states like this. So positive and negative, negative and positive changes the polarization state. You change it applying, reversing the magnetic field, and here you reverse the electric field. So theoretically, and these two materials have their own applications, like a ferroelectric random access memory or the recording media. Okay, so if we can combine these two properties, already you can see that D0 and Dn. There are two different, very important parameters here. But you want to combine these two properties. That means you need to understand what kind of mechanism do you need to introduce magnetism or the ferroelectricity. So basically, we want to have the P, M, and He, so that you can have a cross coupling between the two, electric field, and then magnetism. You apply electric field and then change the magnetization, or apply magnetic field and change the polarization. You need a very strong coupling between the two order parameters, and that will help you. For example, right now we are using the current to make the recording, and if you use an electric field with a small field, you will be able to write, so you can save energy. That is one of the application envisaged for this kind of multiferroic materials. There are so other applications like spintronics and other sensors and other devices possible. But let us not go into that, because we need to understand the materials aspect, and my expertise is more on materials aspect. So that's jumping. So yeah. So as I mentioned to you, symmetry is very important. So I am sure that most of you know various symmetry elements or symmetry operations. An object is said to be symmetric with respect to transformation if the object, after the transformation, appeared to be in a state that is identical to its initial state. That's what the symmetric, when we say symmetric. A symmetry operation is the motion of an object into a position that is indistinguishable from its original position. So that is the symmetry operation. So we have various symmetry operations like a translation. As you know, in crystals we see rotation, reflections, inversion. So all of these three are a point symmetry, because we are operating this about a point. And there is also roto-inversion or roto-reflection, which means a rotation followed by inversion. or rotation followed by reflections. Okay, so these are improper rotations or improper symmetries. And other than that, you have which translation involved screw rotation or spatial symmetry operation, which is screw rotation and then glide reflections. So this is what we study in the normal crystallography, which is very important to understand the structure, because the symmetry is useful to determine the structure and also to predict the properties, because there are several properties that depends on the symmetry of these crystals. Okay, I will just, for the continuity, I will just introduce some symmetry operations here. And here there are, here you can see one object. There are two objects which are related by twofold rotation, and this is the symbol for twofold rotation. This is the rotation axis, and you can rotate by twofold, means it's at 180 degree, and this object moves here. So these two objects are related by twofold rotation, and the twofold axis is along this direction. Same way, you can have threefold rotation. What we called is a 3 in Hermann-Huygens symbol, or C2 in Sonnenfleisch symbols. So in crystallography, we use the Hermann-Huygens symbol by 3 or 2. Okay, so threefold axis, this is the symbol, and then goes here, and the next rotation it goes here, and then it comes back to here, original position. Same way, you can have a 90-degree rotation. Okay, so that we call fourfold axis or sixfold axis, and so on. And we can have mirror plane. So the mirror plane can be in different axes. What is shown here is an object, and then this is the circle, that is the mirror plane axis. And if you apply a mirror plane, and you can see this comes down. Okay, so this is the mirror plane symmetry. And inversion is about its center. So you have an object, and then you join this to the center in the same distance in the opposite direction, and you extend, and if they are related, and you see this is an inversion axis, which is 1 bar or I, it is denoted as that. So these are all the crystallographic symmetry, point symmetry operations. And you know this roto inversion and roto reflections, which means rotation followed by inversion. So for example, 3 bar, what it means is a threefold rotation followed by inversion. The bar means inversion. So you have to do threefold rotation, which means it will come here, and then followed by inversion, so it will come here. So these 2 points are related by 3 bar rotation. Okay, and the same way you can have a fourfold rotation and then followed by inversion, which is called 4 bar. So you have fourfold rotation comes here, and then inversion comes here. So these 2 are related by 4 bar symmetry. Same way you can have 6 bar rotation, and so on. Interestingly, you will see here 2 over m, which means you have twofold rotation perpendicular to the rotation axis. You have mirror plane. So we can take here, you can see the symbol. So for twofold rotation, you like a diamond, like a completely filled diamond, like symbol, and here at the center you have the white. So a hole on this, which means it is an 2 over m. So for example, here you have twofold rotation, and then perpendicular to this you have this mirror plane. So that will bring here. So you are doing only twofold rotation, and perpendicular to that twofold axis you have a mirror plane. Okay, so yes. Okay, so you see that 4 objects. Now you can see an inversion center at the center through the center. Okay, these two objects are related by the inversion center, but which is not obvious in the point group 2 over m. But you can understand that when you operate twofold rotation perpendicular to the mirror, perpendicular to the rotation axis, a mirror plane, you generate an inversion axis. So whenever there is a perpendicular mirror plane, you get an inversion axis. Okay. Okay, so we know that the various symmetry operations can be combined in certain manners. Now you cannot combine in all random. So if you do it, what you end up having is 32 crystallographic point groups. Okay, so so these point groups can be classified into different classes, like a 20 non-centrosymmetric, okay, which is piezoelectric, and there are centrosymmetric point groups, okay, and also out of 20 non-centrosymmetric, then you have the 10 polar pyroelectric point groups. So these, not all centrosymmetry can be a ferroelectric or pyroelectric. Okay, so only polar classes, polar or pyroelectric class of symmetry materials can be a pyroelectric or ferroelectric. Not all centrosymmetry can be, but those non-centrosymmetric materials can be piezoelectric, but not ferroelectric or pyroelectric. So, and there is one class up at 432. Okay, and you can see these are all called enantiomorphic or chiral point groups. Okay, and you can further divide into optically active chiral groups like a plus M, MM2, -4, -4, 2M, all these groups. So it's very important to understand the point groups and their classifications. And you need to really understand material, what point group your material has, or what space group when you introduce the lattice, and you will understand what kind of space group your material has. Okay, so as I pointed out, why we need to understand the symmetry aspect when we are looking at the physical properties of materials. It is important to not only characterize the crystal and also the magnetic structures, okay, because the magnetic structure also tells you, particularly in the case of now magnetoelectric and multiferrite materials, the magnetic structure is very important. So, and symmetry is fundamental for that crystal structure and magnetic structures. Interesting physical properties such as piezoelectric, ferroelectricity, second harmonic generation, and optical activity like rotary polarization, all this comes, there is a requirement that absence of inversion symmetry. So that means you cannot have a material with inversion symmetry and look for this kind of properties. So it is very important to understand this. Sometimes what you do, sometimes you cannot find out whether your system has center of inversion or not. Sometimes you do other way. You measure the ferroelectric or piezoelectric or second harmonic properties, and if you say it is positive, then you can find out between two space group. One is centrosymmetric and non-centrosymmetric, and most of the situation you will end up having that such a situation, like from X-ray or sometime in neutron also. Sometimes it's difficult to find out between centrosymmetric and non-centrosymmetric. Then you can do this kind of experiment, and then you can say that yes, my sample is centrosymmetric or non-centrosymmetric. So you can do the other way also. But it's most important to you understand the symmetry aspect of these materials. So symmetry of physical properties of crystal must include symmetry of the crystal. So it's a very important theory proposed by Newman. So it's called Newman's principle or principle of symmetry. So this is basically based on the symmetry. The physical property must include the crystal symmetry of the crystal symmetry. So it's very important. So let's not go into, I assume that you know some crystal structure and then symmetry, but I have given you a small introduction about it. Now I go into magnetic symmetry. So when you say magnetism, you come across this kind of magnetic structure, very common. There are more than 1,000 type of magnetic structures possible. Okay, we get it from, I understand, from the neutron diffraction. So you can see these are some examples, typical textbook example. You can have a collinear ferromagnet. All the spins are aligned in one direction. So this is the ferromagnetic material, what you see. And then collinear antiferromagnet, up down configuration. So you can have it in three-dimensional, or there are different kind of antiferromagnetic possible spin configuration, but the net moment will be zero. Either you can have near neighbor magnetic moments are aligned in opposite direction, which we call G-type antiferromagnet, or you can have a A-type antiferromagnet or layered antiferromagnet, which means these layer will be like this, like a ferromagnetic. The next layer will be ferromagnetic, but these spins all will be down. Okay, the next layer will be up, next layer will be down. So this is antiferromagnetic. Okay, so this we call G-type antiferromagnet, and this kind of layer antiferromagnet we call A-type antiferromagnet. Like that, you have E-type antiferromagnet, and different configurations are possible. There are C-type antiferromagnet, and so on. So you can have a column, like this, up, 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 and this one will be down, down, down. So you can have a C-type antiferromagnet like that. Okay, and you can have a non-collinear. These are all collinear magnet, and you can have this kind of non-collinear magnet that can generate a weak ferromagnetic moment, a weak moment. But here the net moment is zero because they are collinear. But the non-collinear magnetic structure you can have because of the canting. What we call the spins are not collinear, so they are producing a finite magnetic moment. We say that it produces a weak ferromagnetic moment or weak moment. Okay, so there is a finite magnetization. Then also very complex magnetic structure possible. Helical antiferromagnet, it can rotate, in the plane which may propagate, which is parallel or perpendicular to the direction of the spin moment. So based on that, you can say it's a cycloidal moment or spiral, or you can have a spin density wave. There are quite complicated magnetic structure possible. We need to also understand why such kind of different magnetic structure exists. Like particularly the complex magnetic structures, like even in the ferromagnetic means it's only one ferromagnet. That's all of them in the same direction. Or you can have a perimagnet. That means this layer can be a large moment, and this can be in opposite direction, but not same equal magnitude, but small moment. Okay, like in Fe3O4. So we can have. But in all other antiferromagnets, these are all antiferromagnets. We can have quite complicated magnetic structure that depends on the your crystal structure and the magnetic moment and the arrangement of atom in the lattice. Okay, in many times the magnetic frustration which can cause, in most of these oxide materials you have antiferromagnetic superexchange interactions. Okay, and the kind of superexchange lead to different kind, and then electronic configuration that lead to the ground state magnetic structure, which are different from for different compounds. And particularly what we are interested in magnetoelectric materials is one is collinear antiferromagnet, the another is this complex magnetic structure which is mainly caused by magnetic frustration. Okay, that means they are not very the superexchange interactions involve at least two different exchange interactions. You can have a nearest neighbor ferromagnetic, and then next nearest neighbor antiferromagnetic, and so on. So you can have a various magnetic exchange path and competing exchange paths that can lead to this kind of ground states, and that exhibit very interesting physical properties. And that is the origin of ferroelectricity in some of the magnetic materials. I will come to that later. So magnetic moments are often visualized as arrows. That's what we write like above like that. But for our understanding, it is more useful when we say that in a current loop, like a classical classically we describe this magnetic moment in a current loop. When we have right hand rule like this, so when you see that, hold it, but I cannot show. So but you can imagine that the arrow in the plane, okay, and the current is moving in this direction, your magnetic moment is pointing up. You change the direction of the current, then the magnetic moment will point down. Okay, this we also call, this is a time reversal. So time reversal symmetry. So when you change the current directions, and magnetic moment will be reversed. This is one of the symmetry operations that we are going to add into the crystal structure symmetry operations that will multiply the 32 point group into 90 plus, and then 122 total magnetic point groups. So okay, so we know crystallographic point group, two-fold rotation. What is it? Just two-fold rotation means 180-degree rotation, and you will see one point is after that. So you know the correlation between the two. Now I'm going to show you the same thing you can apply to magnetic moment. For example, here what is shown is a twofold rotation. Here the red sign on the left hand side is the magnetic moment, and the current loop is shown here. And this vertical bar is the twofold axis. When you do a twofold rotation, the spin moment direction remains the same. But when your magnetic moment is perpendicular to the twofold axis, you see that magnetic moment direction is reversed. Okay, which means your magnetic moment and your rotation axis. So with respect to, so it's very important which axis you are applying, or with respect to twofold rotation axis, what is the direction of the magnetic moment. So, but in the case of mirror plane, you can see there are again the two cases possible. In one case, if the magnetic moment is parallel to the plane, okay, what you see because of this current loop, it is reversed, so you can get the magnetic moment is reversed. Okay, but in the other case, okay, so you can see the magnetic moment is perpendicular to this plane, and in this case it remains the same. Okay, so in the twofold axis and mirror plane behaves in a different way with respect to the direction of magnetic moment to the twofold axis or mirror plane axis. And it's very important to look at the inversion axis here. So when with respect to magnetic moment, if you do an inversion, the magnetic moment does not change its direction. It remains the same. Okay, you can see that this point will come here. So any point if you reproduce, that will come here. So that means the current direction does not change, so the magnetic moment does not change. But when you do a time reversal, which I just mentioned in the previous slide, so if you take this kind of a current loop and magnetic moment, if you do a reversal of this, so obviously you change the direction, so the magnetic moment direction will change. So this is a non-spatial symmetry operation. So you can see that in the magnetic moment with respect to inversion remains the same, whereas the time reversal, it changes the direction of the magnetic moment. So in addition to rotation, mirror inversion operations, time reversal operation can be a symmetry operation in magnetically ordered materials. So in the paramagnetic state, okay, so there's you don't have the time reversal operation, but when you introduce in the magnetic state, in the ordered state, then you can apply the time reversal symmetry. Okay, but otherwise it is existing in paramagnetic state. Basically, you have up spin and down spin. Okay, but in the below the magnetic ordering state, it is not the case. It may follow or it may not be, depending on the spin configuration. We will see some examples for that. So I just want to take one example of a magnetic point group, which is twofold axis, just twofold axis. So what the crystal system, it is monoclinic. You can say from the point group what is the crystal system. So it is a monoclinic point group. So you have one atom here and twofold axis is here and it comes here. That's a crystallographic twofold axis. Okay, so and we have a spin, it's the same thing we saw in the previous slide, so it does not change. Okay, but here this also we saw that, so if you have a spin perpendicular to that, but it changes the direction. But you can see on the right hand side 2, and we have put it's a prime, okay, which means the time reversal operation. You have 2 spins which are perpendicular, which are in opposite direction. So if you want to satisfy this, so what you need to do is a twofold rotation will bring it here in the same direction like this, and then you operate the time reversal that will reverse the spin direction. So this is nothing but a twofold rotation followed by time reversal symmetry. Then these 2 spins, these 2 are related by 2 prime. Same way you can say this material, this spin configuration which is perpendicular to that. So now you apply twofold rotation, that means it will be like this. So here it will go this direction, the arrow will be along this direction. Now you apply the inversion, time reversal, so it will change its spin direction. So it is parallel. Okay, now you have the time reversal operation here. So you have the time reversal operation here. Okay, so this is what. So the introduction of the time reversal operator increases the number of classes by adding 90 additional magnetic point groups. That's why your number of point groups is increased when you increase the time reversal operation. So for example, here you have this two-fold rotation, just one, and that has made this all this four. Two with respect to spin along this direction or this direction, it matters, whereas here it is not matter at all. But when you add prime, which is time reversal, whether it is parallel to two-fold axis or perpendicular to two-fold axis, you can have different configuration, spin configuration. Okay, so now let us look at magnetic symmetry and then see how it distinguishes from the crystallographic point group. So this one is 2 over m. 2 over m is again monoclinic. We saw some time before. That means a two-fold axis. Perpendicular to that two-fold axis, you have a mirror plane, but it also contains inversion axis, which is not obvious. But when you do two-fold axis perpendicular to mirror plane, you see there is an additional inversion axis is generated. Okay, but you can see in addition to that, this is the paramagnetic or crystallographic point group, which has 1 prime, we say that, which is nothing but just time reversal operation. That is containing both regular and time reversal symmetry. So we have upspin and downspin. That's what the time reversal symmetry changes. So if you have upspin and putting the time reversal symmetry, it changes the spin direction. So now we can see how many possibility in this case, 2 over m. Okay, so there are 4 magnetic groups associated with crystallographic point group 2 over m1 prime. So what are those? 2 over m, okay, which contains 2-fold rotation and then a mirror plane and then an inversion axis, so which is not obvious. Okay, but not 2 prime, not m prime, not 1 bar prime, which is inversion axis followed by, which is or we can say this is an inversion center followed by time reversal. So but you can see here next one is 2 over m prime. That means two-fold rotation perpendicular to that mirror plane, then you have the followed by time reversal symmetry. What it contains? A two-fold rotation, m prime, and then 1 bar prime. So the next one is 2 bar 2 prime over m. So this contains obviously 2 prime and mirror plane and then 1 bar prime. And then the last one is 2 bar 2 prime over m prime, which contains 2 prime, m prime, and an inversion center. Okay. Now, what is shown here is the representation of the point group. As you know, when you study the crystallographic point group, you will know that this is represented by the projection of the sphere, and basically this is a circle, and 2 over m. This point group is represented like symbolically characterizing. Okay, for example, here two-fold axis. In the monoclinic structure, you have the B axis is the unique axis, so that is this two-fold axis. So you have the two-fold axis here. You can start any one of them, like here. That means it is above this the plane. Okay, now you rotate about this axis, so this will come here, but it will go below. Okay, now perpendicular to two-fold axis, which means this is the two-fold axis perpendicular to this. I put a mirror plane here. So that means this symbol will come here and this object again will come here. Parallel. Okay. Now, do you see any center of symmetry? Of course, these 2 points are related by center of symmetry and these 2 are related by center of symmetry because one is above and another is below. So you have center of symmetry. But now we come to time reversal, which is prime, 2 over m prime. So you have the two-fold axis. Okay, so this comes here. Now you are going to do m prime, which means you are going to put a mirror plane. So when you put a mirror plane, it comes above, but instead of circle, it becomes square. What does it mean? It changes from the time reversal operation is added. When you do time reversal operation, the spin changes. That means the spin was up, for example, it is parallel, and then when you do time reversal, it will change its direction, spin direction. Okay, so it's like that. So you can also, this also like this. So when you do that, So you have time reversal operation and it changes the spin direction. Now you can see between these two, there is no time reversal is centrosymmetry is broken here. Okay, this is a very important symmetry requirement for to find out ferroelectricity to have the magnetoelectricity and multiferroic effect. Okay, I will come to this a little bit later, but let us see 2' by m. So 2' means twofold rotation. That means it will come here, and then followed by you have the time reversal symmetry. Okay, so you start with here, and then it goes below, and then it changes the direction, spin direction. So that is 2 bar, and then you put a mirror plane, and it will not change. Okay, so now again you have the inversion symmetry is broken here, and in this case, the last case, 2' over m'. So this is the 2', so the same thing operation you have, and then m' operation, whatever you have done here. So you will see this as a centrosymmetry. Okay, so to have a magnetoelectric effect, what we need is the inversion symmetry broken. So only material with these two symmetry point group. Okay, these are the 4 magnetic point groups. Out of that, only these 2 point groups allow magnetoelectricity. You cannot take a material with this spin configuration and say it is magnetoelectric. There is something wrong. So, for example, DY-OH, okay, or RBM-OH, these materials are linear magnetoelectric because they order at low temperature around this is around 4 Kelvin and 6 Kelvin or so. They are antiferromagnetic, okay, and they have the spin structure, and that is characterized by 2 over m', and this spin structure is characterized by 2' by m. So that is the magnetic symmetry. That magnetic symmetry should break the inversion symmetry. Okay, the magnetic point group should break the inversion symmetry. Then only this material can show magnetoelectric or multiferroic effect. So it is very important for this to find out the magnetic structure of that compound. So without knowing the magnetic structure, because many times you do measurements on polycrystalline sample or even single crystalline samples, because these polarization coming from this magnetoelectric and multiferroic materials are very less compared to typical ferroelectric material, and many times these measurements go wrong. Okay, it misleads. So it is very important to look at the magnetic structure of the material and understand the point group symmetry of the material, whether it is centrosymmetry is broken or not. Okay, so without doing that, we have to be very, very cautious. So, and typical, I just want to give you example because it's taking too much time, I think. So I will go forward. Simple example is alpha Fe. Alpha Fe is a body-centered cubic at the paramagnetic state. Okay, but below the magnetic ordering state, you can see 4 over m', which means it is tetragonal. Okay, so what happens below the magnetic ordering? You can see this, all the spins are up, including the body-centered one. Okay, that is the ferromagnetic configuration, but the symmetry has become Im3m to 4 over m. This is the point group. Okay, so which means it is tetragonal. So the symmetry is lower because of the magnetic ordering. So the symmetry goes to one of the subgroups of the paramagnetic or crystallographic point group. Okay, that's what you will see, and this corresponding the representation is this. Okay, and this material obviously has a center of inversion, and this cannot be a magnetoelectric. Okay, and another example is the cobalt. Okay, cobalt is hexagonal, you know, and its magnetic symmetry is 6 over m'. So we need to know what is the magnetic structure and its corresponding magnetic point group, and we need to see whether there is a centrosymmetry or not. Okay, now I told you that when we add time reversal symmetry into the 32 point group, we get additional 90 magnetic point groups. Okay, and out of that, so totally we have 122 magnetic point groups. Out of that, only 58 point groups allow linear magnetoelectric effect. I will tell you what is linear magnetoelectric effect. Okay, so and this is the magnetic point group given here. You can see for each crystal system, one bar prime. The magnetoelectric coefficients are given here, and these are the generating elements. Okay, the symmetry elements and its directions. And you can see that one bar which has inversion, so it is not magnetoelectric. Magnetoelectric coefficient is 0, and the other two contain some value of magnetoelectric coefficient. Similarly, monoclinic system, you can see out of all these point group, magnetic point group, these two contain center of inversion, and therefore these two are not magnetoelectric, and rest of them are magnetoelectric. So you cannot take a material, magnetic material, which is characterized by either 2 over m or 2 prime over m prime, and claim that this material has a magnetoelectric effect. So that's not correct. Symmetry is really good. Symmetry has to allow the movement of the charges. Okay, then only you can get magnetoelectric effect. The same way, orthorhombic system. These are the various magnetic point groups possible. Out of that, these two are non-magnetoelectric, like that trigonal point group and so on. Okay, so now let me proceed. I think that is a very fundamental thing one needs to know, and I don't think many places people talk about the crystallographic point group and magnetic point group and its importance to understand magnetoelectric effect and multiferroic. So now I will go into magnetoelectric effect and multiferroic, give some two examples. Okay, so first let me start with magnetoelectric effect. People sometimes use magnetoelectric and multiferroic without knowing what is it. Okay, and as we know that these magnetoelectric effects are more than 100 years old. It was predicted by Pierre Curie a very long time before, it is possible to induce a magnetism in an insulator by bringing an electric field or vice versa. So that's what's shown here. For example, magnetoelectric effect is nothing but induction of polarization by applying a magnetic field. Normally, in ferroelectric material, you apply electric field and change the polarization, electric polarization, or apply a magnetic field, change the magnetization. But here, what we are doing is something which is different, which does not come in the Maxwell's equation, as you know. So if you apply a magnetization, you apply a magnetic field and change the electric polarization, or apply electric field and change the magnetization. Okay, that's what we are saying, magnetoelectric effect. Okay, a cross coupling of these things. So this is, for example, a pictorial representation. You have an insulator, you bring a magnet and induce a voltage. Okay, here the P, whatever polarization is proportional to magnetic field, and this is alpha ij, which is the linear magnetoelectric coefficient. Or you can have the vice versa effect, that you apply an electric field to a material and you induce magnetization. That is M proportional E. So this kind of effect, a cross coupling between the magnetism and electricity, is possible in materials. So that was predicted very long back, but it took more than 100 years, and it was only 1958 or 1960, after the prediction based on symmetry consideration in chromium oxide, it really picked up this field. Otherwise, it was at the birth only, even 50, 60 years after predicting this kind of possibility in materials. So this is the equation, all you know, that free energy equation in terms of electric and magnetic field. You can expand like this, which is the ground stem, and then you have the typical polarization, and then electric field, magnetization, and the magnetic field, and your electric susceptibility, electric fields, and then similarly magnetic susceptibility, and so on. The most important right now what we are looking at is the alpha ij ei hj, which is the linear magnetoelectric term here, linear coupling between the electric and magnetic field. And there are also higher order term, okay, which contributes to the ferroelectric effect or the polarization. Okay, so when we differentiate this with respect to electric field or magnetization, you can have this relation Pi, for example, dou F by dou E. You can see this the polarization which is coming, and importantly the alpha ij goes in a magnetic field Hj. Okay, and similarly you can have the magnetization in terms of electric and magnetic field when you differentiate, and then you can have this alpha ij in terms of electric field. So we are interested here in linear magnetoelectric coefficient. Okay, so when you apply an electric field, you induce change, and you see these electric coefficients. Normally in linear magnetoelectric materials, this coefficient is very small. So when we look at the symmetry aspect, as I told you, what is the symmetry requirement for a multiferroic or magnetoelectric effect? So for a material to be magnetoelectric or multiferroic, what you need is there's still a subtle difference. So you have this electric field plus minus, okay, a polar vector, and then axial vector, which is the magnetization here. Okay, so you can do an inversion, but what we say is a even function for or spatial inversion or odd function with respect to time reversal symmetry. So we know that P equal to, which is alpha or the coupling between these two terms, okay, magnetoelectric coupling, and this is the magnetic field. Okay, this alpha ij, you can take it like this. But what is the symmetry of this? So what is this symmetry should be satisfied for a material to be magnetoelectric? So it should break, for example, both space inversion and time reversal symmetry. Okay, that is the main condition. That's what shown here. So you need to break both spatial inversion and then time reversal symmetry. And the magnetic point group, I told you there are 122 magnetic point groups are there. Out of that, only 58 point groups allow linear magnetoelectric effect. Okay, so one example I want to tell you, very historic in this system, and this was predicted by Zylowzinski in 1959 based on the symmetry argument. So you can see that very important that Cr2O3 and Fe2O3, both system, the crystallographic structure is a corundum structure like a Al2O3 structure. It's a rhomboidal structure. Okay, so the crystal structure is same. It's a centrosymmetric. Okay, but when it undergoes antiferromagnetic ordering, the antiferromagnetic structure of chromium oxide and the antiferromagnetic structure of Fe2O3 are different. You can see the spin structure here on the left hand side, up, down. Okay, this is the center of inversion here. So down. So you have down, down. Okay, about the center, and then up here. But in the case of chromium oxide, up, down. In the center of symmetry, you can see about this. This is down, this is up, and then again down. Okay, so here the center of inversion is retained because the spin does not change. That's what we saw sometime before. Whereas here the center of inversion is broken. That means you can expect a magnetoelectric effect in this material, but not in this material. Okay, so that's what you can understand this. So these are the so in the unit cell of rhomboidal, so you'll have 4 cations, either chromium, 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 and of course you have chromium oxygen octahedra, which are not shown here. So Fe2O3 octahedra, which are not shown here. In the rhomboidal structure, you have 4 ions, chromium ions or Fe3 plus ions, and you can see these 2 ions which are shown here, plus, and then you have oxygen and oxygen. And the distance will be, when you don't apply any electric field, the distance will be same between the two about the center, and d1, d2 equal to, so there is no electric dipole moment, or there is the magnetization also equal, okay, up, down. So E equal to 0, you have no polarization or no magnetization. But now when I apply electric field, E not equal to 0, what happened? They will just move, okay, in this direction, So one is close to this oxygen, one goes farther away from the oxygen. So this makes an effect because the symmetry allows here. Further, it changes the orbital motion of the electron. That changes the cause of the magnetization as well as the electric polarization. Okay, so applied electric field. Okay, and this can when D1 not equal to D2. That means you have the finite dipole moment appearing or polarization appearing due to that. So, okay, but this is not possible here because that has the center of symmetry. So you can say from the symmetry of the magnetic symmetry of the Cr2O3, the magnetic ordering is around 307 Kelvin. So at room temperature, it is really magnetoelectric. So you can say that Cr2O3 is magnetoelectric, whereas Fe2O3 is not magnetoelectric, based on the symmetry. And that's what he predicted. So immediately within a year, two independent groups, Astro and Redo, they showed, this at 300 and below 307 Kelvin, you can see the magnetoelectric susceptibility and the temperature. You can see this is the delta M induced by electric field, the circle, and delta P induced by magnetic field. So when you apply a magnetic field, you induce electric polarization, or you apply electric field, you induce magnetization, and this appears like this. So that is the linear magnetoelectric effect. Okay, but you need to apply electric field and magnetic field in this case to observe. As I told you that because it's coming from the orbital motion change and the electrical susceptibility or the polarization, which is very small in this case, and that is limited by this relation. And that's why people thought that when we make a ferroelectric material and ferromagnetic material, and you can combine these two, then you can have a large magnetoelectric susceptibility. Okay, and that is the birth of multiferroic. So you want to combine ferroelectricity and ferromagnetism. So now I want to classify this ferroelectric multiferroic in a different type. Okay, so already you can see in the literature there are type 1, type 2 multiferroics, but recently, based on my investigation, I want to introduce another class of material which I call type 3 materials. So what is this new? I want to tell you. Type 1 materials are polar, which means the crystallographic structure is already polar, like a BiFeO3. It is like a barium titanate. It is polar. Okay, so it is R3M. So it's a polar space group or polar point group, which means you expect it to be ferroelectric or pyroelectric. Okay, pyroelectric or ferroelectric. So all these materials, but this has not been really shown to be because of the leakiness of the system. People really could not show whether it, and there are also counter argument saying that this is a centrosymmetric system. But clearly BiFeO3, everyone accepts that it's a ferroelectric system where the lone pair effect of bismuth, okay, induce polarization, whereas Fe gives magnetization. Okay, in barium titanate, the titanium moves towards one of these oxygen, then it makes a dipole and they order, and that gives rise to polarization. But here, bismuth lone pair, that gives you, because of the hybridization with the high energy orbitals with oxygen and 6s p orbitals, and that gives you a polarization. Whereas it is not necessary always that if you have a lone pair, that will be a polar material. There are many material which are bismuth chromate, for example, which is non-polar, whereas bismuth FeO3 is polar. I think people now understand BiMnO3 is also non-polar. Okay, and what happens though? So they are ferroelectric material. The very high Curie temperature, ferroelectric transition is close to 1000 Kelvin. But at low temperature, like Fe undergo magnetic ordering around 640 Kelvin, whereas ferroelectric ordering temperature is very high, close to 1000 Kelvin. But there are two different temperatures. One is ferroelectric ordering temperature, another is magnetic ordering temperature. But it is antiferromagnetic, it's a spiral ordering. So And because of these two different temperature scales, the coupling between ferroelectricity and magnetism is weak in these materials. Okay, and it is possible in lead, vanadate, and so on. So this we call a type 1 material. There are also YMnO3, and it is because of the yttrium displacement due to geometric frustration. This is an hexagonal structure. It's not perovskite structure. There is a trigonal bipyramid configuration of manganese. Okay, and this geometric frustration tilting of this leads to yttrium displacement that gives you a polarization. So this again, you have ferroelectric ordering temperature high and manganese ordering temperature at low temperature, below room temperature. So again, the coupling is weak. Okay, but you have two ordering temperature in this case, but this is also a polar system. That means it is ferroelectric at room temperature, ferroelectric at room temperature. Okay, but the coupling is weak in these materials unless you introduce some kind of strain in thin film or something. It is possible to have coupling, but in bulk materials this coupling is very weak. Okay, next is a type 2 material which is non-polar. These materials are centrosymmetric materials like a TBMnO3. It's a centrosymmetric. It's an orthorhombic perovskite, and this is also perovskite, but polar system. Okay, it is because of the bismuth lone pair. But terbium manganite is an orthorhombic perovskite, PNMA space group, which is centrosymmetric, or COCr2O4, MnWO4. All these systems are centrosymmetric. In the paramagnetic state, they are not ferroelectric. So what does it do? Induce polarization is they undergo magnetic ordering at low temperatures. Okay, and those spin structure which I showed you sometime before, they are complex spin structure coming because of the magnetic frustration, and that frustration exists in all these materials. That leads to a complex spin structure below the magnetic ordering temperature. So that spin structure induces ferroelectricity. Okay, there are various mechanisms how the ferroelectricity comes, we can see later, but the spin ordering itself induces ferroelectricity. But we saw in the classical barium titanate, you need D0 ion to get ferroelectricity. But here you see a magnetic ordering itself induce ferroelectricity. The only disadvantage is that the ferroelectric polarization, it is at least two order, it is 100 times, it is lower than in the ferroelectric, typical ferroelectric material like a bismuth ferrite or barium titanate. Okay, so that is, but the coupling is very strong because the ferroelectricity is induced by magnetic structure. So when you apply a magnetic field, you change the magnetic structure, you induce also change in the polarization. So the coupling is very strong in this material. So for practical application, type 2 materials are interesting, but unfortunately the magnetic ordering occurs at very low temperatures. So we need a good magnetic material which orders at very high temperatures and which gives you polarization, that is a spin induced polarization that we call type 2 multiferroid. In type 3, what I classify is the materials are like A2MO3O8 and CaBaCO4. I'm sure that Professor Kiran also co-author of this, and you can see this space group PBN21. Okay, and this is P63MC. This is again polar. This is like this, type 1. Okay, but there is a difference here. I will tell you what is the difference. This is also polar and this is also polar. Type 1 is polar, type 3 is polar. But in type 1, there is a paraelectric to ferroelectric transition. There is a Curie temperature here at 1000 Kelvin, for example, here. But in these materials, there is certain kind of ordering of ions. Okay, here this molybdenum 2+, 3+, they have or they can have a different kind of coordination. For example, they can order in certain manners that we call chemical ordering. This chemical ordering can break the inversion symmetry. When the chemical ordering occurs, when you make the material,
at that point of time it forms. That means the melting point is the temperature at which the non-centrosymmetric or polar structure comes. That means there is no non-polar structure at high temperature. Unlike unlike these materials, they undergo a polar to non-polar structure. At high temperature, non-polar structure, as you cool, like a barium titanate, is cubic at high temperature. You cool it to room temperature, it becomes tetragonal, which is polar. Same way bismuth ferrite. So it is polar at low temperature. At high temperature, you heat it to non-polar, then it may decompose, or melt. But these materials, it directly goes to the melting or decomposing. Okay, that means these polar structures are formed right at the formation temperature. So what is the effect of that? So for example, here there another class of material which we introduced, we discovered this material RFPWO6, that's also PNA21, a polar space group. All these materials are pyroelectric, they are not ferroelectric. Because of this chemical ordering, you will not be able to switch this polarization in these materials, though they are pyroelectric, they are not ferroelectric, whereas type 1 materials are ferroelectric. So that is the difference. I call this type 3. Then when these materials undergo magnetic ordering at low temperature, it induces a change in electric polarization. This polarization, you can sometimes reverse the polarization below the magnetic ordering. So the magnetic ordering can induce another polarization, or it can enhance the paraelectric polarization. Okay, not paraelectric, paramagnetic polarization. That means the pyroelectric state polarization. Okay, so that's how these materials are differing from type 1 materials. So that I try to classify as a type 3 materials. They are pyroelectric, non-switchable at the paramagnetic state. But below magnetic ordering, there is a change in polarization, ferroelectric polarization, that can be switched. And the polarization direction can be different for depending on the space group. For example, here it is PBN2, and I think in 2 space groups, you can see along the C direction, the 2-1 axis, that is the polarization axis. Okay, so this time is up now, it's going another 15 minutes, 20 minutes. So I can tell you that quickly, spin induced ferroelectricity. So I told you that bismuth ferrite is the type 1 material, and spin induced ferroelectricity can come from this kind of complex spin structure. This is the sinusoidal or spin density wave structure, or you can have a screw structure like this, okay, in this plane but propagating in this direction, or a cycloidal structure, okay, so it is rotating and propagating in this direction, and the polarization can appear in this direction. So this is explained by the inverse Zylowsinski-Moria interaction. Because of the 2 spin canting, it can displace the oxygen in between the cations, the spins, and that can align in the same direction, can induce electric polarization. So the cycloidal structure of spin is known for this. And there are also conical structures like a conical 1 and conical 2. So you have transverse conicals when you apply a magnetic field, and you can also change this, and this also can induce polarization. So this kind of complex magnetic structure, it is possible to induce magnetic polarization. Sometimes it is also possible to induce polarization in the screw type when you have a charge ordering kind of along this axis. Okay, so this is the cycloidal spin structure. A typical example explained by the spin current or inverse Zylowsinski-Moria interaction. You have these 2 spins, canter spins. Okay, this is a cycloidal. So this is a counterclockwise spin, and this is the clockwise spins. So when it is clockwise, counterclockwise, the spin delta P is like this. So it moves in this direction. The polarization can be switched in the clockwise direction. When the spins are changing to clockwise, then the polarization will be changed to other direction. So you can switch the spin direction based on the spin chirality. So in a simple cantor antiferromagnetic structure, you can see this between the 2, this is, okay, one is up, another is down. That means it is cancelled out. So most RFeO3 system,
most RCRO3 system, they are all belong to this kind of Cantor antiferromagnet where the centrosymmetry is retained. So, which means it cannot become real ferroelectric. Okay, this cannot become multiferroic. Only this cycloidal spin structure can give you ferroelectricity and therefore multiferroic. So this is a typical example for type 1 BiFeO3. So this is the crystal structure, and the Curie temperature, ferroelectric transition is 1100, the Tn is 640 Kelvin. So obviously the coupling is weak in these materials, in the bulk materials. Okay. Now I go to RMnO3. I will give one example for type 2 multiferroic, which is the terbium manganate. So if you look at RMnO3, is a very interesting system. People have looked at for giant magnetoresistance by substituting R site by divalent ions. You can make a kind of Mn3 plus and Mn4 plus ions, and that can induce a ferromagnetism. Okay, and you see large magnetoresistance. So this kind of study is known, but the ground state material without substitution shows very interesting aspect. So lanthanum is rhombohedral, but as you go on this with samarium, europium, gadolinium, terbium, you see this is a orthorhombic structure, a perovskite structure, and this tilt angle changes depending on the size of the A cation, rare earth cation. So the bond angle will change. Manganese, oxygen, manganese. So that will change the nearest neighbor and next nearest neighbor diagonal axis. That is the ferromagnetic and then antiferromagnetic. And that induces a competition, a magnetic frustration that induces, for example, a bigger rare earth ion like samarium, you have a layered type antiferromagnet. These are all ferromagnetic. Next layer is ferromagnetic, but opposite. So it is antiferromagnetic, layered antiferromagnet. But when you go to this kind of gadolinium and terbium particularly, you see it undergoes a spin density wave, okay, or collinear, and the spin moment varies, okay, sinusoidal way. But below that temperature, it goes to a lock-in transition where you can see a cycloidal spin structure which I showed you before. But this incommensurate, this structure, the spin density wave is nothing but combination of two cycloids, okay? And here one cycloid is stabilized, and that cycloid induces a spin induced polarization. That means below this temperature you have ferroelectricity. So spin induced ferroelectricity, okay? So this is the terbium manganate. You have magnetization, specific heat. This is the transition temperature that corresponds to a spin density wave. You can see these here. And then at Tc, there's cycloidal configuration. You can see this, and that is shown down here. And electric polarization appears only at the cycloidal ordering temperature, not at the spin ordering temperature, spin density wave. Spin density wave is centrosymmetric. If you look at the magnetic point group, this is centrosymmetric, whereas below this ordering temperature, this is non-polar. The magnetic point group, magnetic point group is polar, whereas here it is non-polar. Okay, so the magnetic point groups become polar. That explains that origin of ferroelectric polarization, and that has been explained by the inverse Szymanowski-Moria interaction or spin current model. The polarization is proportional to gamma, which contains the spin orbit coupling, and Eij is the the vector connecting these two spins, and then Si cross Sj is the spins. Okay, so there is also, for example, I told you TBMNO3 is very interesting system. When you further decrease the size of this rare earth ion, it goes to hexagonal system like OMNO3. But if you put a pressure on the system, synthesize under pressure, you can stabilize this orthorhombic structure. But those systems exhibit different spin structure. That is called E-type antiferromagnet. But even in this case, it is a polar spin structure that also give you a polarization. So this kind of spin structure that induces polarization which is parallel to the A-axis. Okay. So understanding of spin structure, magnetism is very important to study the spin-induced ferroelectricity. Okay, what I'm going to tell you from in another 10 minutes or 15 minutes, I'm going to show you 2-3 systems. So we looked at the so-called green phase, R2BaCuO5. So this system was well studied because when at the time of yttrium barium copper oxide, the ITC superconductor, this phase initially used to form as a secondary phase, a green phase, green color phase. And when you optimize the synthetic condition, then you get a single phase yttrium barium copper oxide, which is superconductor. But this phase is a useless phase. But later people found little amount of green phase adding into the superconductor, it can increase the pinning, flux pinning, and it can increase the critical current density. So it played a role. But other than that, the magnetism is very interesting in this compound because there is a coupling between copper spin, 3D spin, and then the 4-up spin. So in this series, you will see when you change the rare earth, the spin structure is different for different compound. And you can see some materials are linear magnetoelectric, some materials are multiferroic, some materials are not. Okay, so this kind of things are very interesting. But this system is centrosymmetric. Okay, like a type 2 material. Okay, it's a paraelectric, paramagnetic. It's paraelectric because it is centrosymmetric, and paramagnetic state is below the magnetic ordering temperature. I want to show you 2 cases, 2 examples. Okay, what is the table? It shows different rare earth ion. For samarium, what is this? This is a K vector. Okay, which is describing the spin propagation direction 0, 0, 0. K equal to 0, 0. When you have gadolinium instead of R, you have 2 K vector. One is 0, 0 G and 0, 0 half. Okay, one is incommensurate, another is commensurate. At high temperature, it becomes incommensurate and then it becomes commensurate. Dysprosium, there are 2 K vectors, one 0, 0, 0, 0 half 0. Holmium 0 half 0, 0, 0, 0 plus 0 half 0. There are 2 phases coexisting. And yttrium case, it is 0 half half. Erbium case, so you can see that very interesting case, which means there is an interaction between the 4-up electron and copper 3D system. That stabilizes the ground state. But still the understanding is very complex. So what we thought that we should be interesting by looking at the some of these this K vector, we thought some of this system would be interesting for at least this system we looked at it. And we expected that this system should be linear magnetoelectric because it has a K equal to 0, 0 structure. And when we look at the copper, it sits at the local non-centrosymmetric site. That is the requirement for a linear magnetoelectric effect. So we picked up the system, and we also picked up the system because this is the this spin is a incommensurate spin structure, cycloidal structure that can induce multiferroic effect. So this is linear magnetoelectric and this is multiferroic. That's what I'm going to tell you. And this is what we selected based on this magnetic structure. So we looked at the susceptibility, heat capacity. There are 2 transitions, one here and another here. This is the copper ordering temperature. This is samarium ordering temperature. Okay, they order independently. Okay, and this is the structure. But if you look at the orthorhombic structure, copper, a square pyramid. Okay, there is no connection between one copper and another. They are isolated, but there are connection with the samarium ions through oxygen. So it interacts, 2 copper interacts through copper, rare earth, oxygen, again rare earth and copper. So in the interaction path is very interesting, but it's not very obvious, but it's quite complicated to calculate these exchange paths, exchange interactions. But obviously we have 2 transitions. We are going to see the electrical properties. So what you can see here, dielectric constant, when you measure the dielectric constant without applied field, that is 0 field, the black curve. Okay, so you don't see any polarization there. It is okay, but unfortunately you cannot see this. But But when you start applying magnetic field, you can see the dielectric anomaly increases. So at least 9 Tesla is the maximum. Okay, and this is the loss tan delta value. So it's very small. So you can see at that position, you can see that there is a loss corresponding to this, which is saying that it could be a magnetoelectric. So that is if it is not a magnetoelectric, it can be simple magnetodielectric as well. Okay, so that's what we need to see. That what we need to see is we need to measure the polarization. If you don't see polarization at this temperature, then it could simply a magnetodielectric, but otherwise it can be a magnetoelectric. So we measure the polarization, whether there is any polarization. We measure the pyrocurrent. How do we measure? We apply a magnetic field and electric field, cool to low temperature, remove the electric field, but you put zero field and then you measure no polarization. Okay, it is flat curve. And then I put field 0.5 Tesla, 1 Tesla. Then I start looking at there is an anomaly. Okay, pyrocurrent coming, and there is another one here. That is at the samarium ordering temperature. You can see these two peaks are in opposite direction, which means the polarization due to copper and polarization due to samarium are in opposite directions. Okay, so that is very clear in the bottom curve. You can see, you can integrate this, okay, with respect to time and plot P versus T. You can see at Tn, the black curve shows no polarization. Okay, so that is linear magnetoelectric material. You need to apply a magnetic field, okay, to induce polarization. Whereas in multiferroic material, you don't need to apply a magnetic field. Even in zero field, you will see polarization. But in linear magnetic material, only upon applying magnetic field, you will see. So when you apply magnetic field, you can see that it is appearing polarization, and that is increasing with magnetic field linearly. Okay, and so this we have calculated the behavior close to this transition to find out the magnetic what kind of the magnetic structure is possible, because samarium is highly neutron absorbing. So it is very difficult to say this spin structure. We try to look at by samarium enriched isotope, but still it was absorbing too much. So we could not determine the magnetic structure. But you can see, as I mentioned, these pyroelectric currents are opposite. So the samarium ordering temperature, the polarization decreases. So when I plot the polarization at 10 Kelvin, so at this temperature, for example, you can see that it is increasing linearly with applied magnetic field. Zero field, it is zero. And when I apply magnetic field, the polarization increases linearly. This is what linear magnetoelectric effect is. This is what seen in chromium oxide. Chromium oxide is not multiferroic. Chromium oxide is linear magnetoelectric, like this samarium, barium, copper oxide. So we can, but you can also pole opposite direction. You can switch it, the polarization, but always under magnetic field. Okay, so this is the magnetocapacitance around the Nil temperature. Another important which we proposed from our lab is that sometime measuring pyrocurrent can be misleading due to leakage. But if you measure a DC current, what it means is you cool, instead of poling at above Nil temperature, you cool the system to low temperature. You apply magnetic field and electric field, and you measure the current in presence of electric and magnetic field. What you will see is this kind of behavior. Okay, and this is the true nature of polarization. If it is a leakage, you will see a monotonous increase of the current. Okay, only in real ferroelectric material or magnetoelectric material you will see this behavior, and that you can easily, but for that your material has to be insulating highly. Okay, so the time is running, so I conclude for this part that samarium Ba2 is a linear magnetoelectric, K equal to magnetic structure. Okay, this is similar to that of dysprosium. So dysprosium also has the same K equal to magnetic structure. It should break the inversion symmetry. So this also we found that it is linear magnetoelectric. So we actually took this system by just looking at the magnetic structure in the literature and then said this should be magnetoelectric, and indeed we found that it is magnetoelectric. Then I will present one more case, then I will stop within few minutes. When I change from samarium to gadolinium, very interesting. Same structure, but you look at the magnetic structure, the K vectors are different, I told you. The first transition at Tn equal to 11.8 Kelvin and second transition at 6 Kelvin. 6 Kelvin transition is not gadolinium ordering temperature. 6 Kelvin at high temperature it is incommensurate, that is cycloidal ordering temperature, and 6 Kelvin in the undergoes a commensurate ordering, that is 0 half structure. Okay, it undergoes a Lopkin's transition. It's very interesting. When we look at the properties of this, you can see two dielectric anomaly. Okay, one at the incommensurate structure, cycloidal ordering, and another at low temperature. Okay, at 6 Kelvin, dielectric anomaly, and you can see on the right hand side you have the polarization. I lost my cursor. Okay, you can see the polarization at the first magnetic ordering temperature, and again, it is on the same direction. If you look at the pyrocurrent for zero field, the interesting aspect is at zero magnetic field you have a polarization, whereas in the previous case, when you apply magnetic field, then only you see polarization. But here, without applying magnetic field, zero field, you have polarization. Okay, rather when you apply magnetic field, it is suppressed. So this material is multiferroic. This material is polar. That means the magnetic symmetry of gadolinium to barium CO5 is polar, whereas samarium to BaCO5 is non-centrosymmetric. Okay, it's very interesting. The magnetic point group is non-centrosymmetric in samarium case. In gadolinium case, it is polar. That's why it is ferroelectric and multiferroic in gadolinium, whereas in samarium, it is magnetoelectric. This is very important conclusion, and we have seen very interestingly in the same family of material green phase. So that depends on the magnetic structure, magnetic symmetry. One symmetry tells you it is magnetoelectric, another tells you it is multiferroic. Okay, so I think 4:22 now I will stop because I have some more thing, but it's very difficult. So we did neutron diffraction. Gadolinium is again absorbing. So we did at 1.3 Kelvin. So 0 half you can see K vector, and the magnetic space group you see PaCa21, that is polar. So that is multiferroic. That means without applying magnetic field, you should see polarization. That's what we see. Okay, and this is the magnetic structure of the incommensurate structure. You can see a very long K vector 00G. G varies from 0.44 to 0.5 at T Locking temperatures. Okay, the magnetic space group is PM1 prime. So the incommensurate space group is still polar, PM. Okay, also the commensurate space group is also polar. So both these magnetic structures support ferroelectricity and therefore multiferroicity. And the previous samarium is only non-centrosymmetric, it's not polar. That's why it is, but breaks the inversion symmetry. So it is, so you can imagine you have a piezoelectric material and a ferroelectric material. Piezoelectric material is non-centrosymmetric. Ferroelectric material is a polar. You can see a same situation here. Magnetoelectric is non-centrosymmetric, whereas multiferroic is polar material. So this is what I want to conclude. I hope you enjoyed. I will take questions now. I'll stop here. Professor Kiran?
Yes, sir. Thank you, sir. Thank you very much. Very nice and informative talk, and we enjoyed a lot. And you address very well the magnetic point group as well.
Yeah.
Because the knowledge of magnetic point group is essential.
Yes, sir.
So,
that's why I did not want to present my results.
Yes, sir. Yes, sir.
Before
asking any question, really I appreciate, and sir, we learn a lot.
Thank you. Thank you.
Because you will not find all this information on a single talk anywhere.
No. It is my experience. I understood. That's why I said I have to give this talk like this. So,
no, it's very fun. And sir, you addressed a very important point of this 114 system.
Yeah, correct. Your system, yeah.
Sir, still there is many things to explore in this system, because there are two magnetic transition actually.
Okay, I see. Okay.
Here the transition, and there is one recent PRV. They dope the strontium. Because when I did the work on single crystal, and sir, the beauty of this 114 system is, sir, I have not mentioned. I mentioned in that paper. If in case of single crystal, if we cool the sample without any electric field, then also you will see the polarization, pyroelectric current.
Correct. At the magnetic ordering temperature.
Yeah, because so it is really very interesting. And I try to reverse the electric. I try to reverse the polarization on single crystal. But you know that inside the PPMS, we cannot apply very high electric field.
Oh, okay, under magnetic field. Okay.
Yeah.
But electric field switching was not possible, no?
It was not possible. Sir, I saw some change, but I was unable to switch it completely. And that time I left France and I came.
Yeah.
Okay, so sir, thank you very much. I will take the question from the audience.
Okay.
So first, Mr. Mukesh, you raise hand sometime. So from this Microsoft team who want to ask the question, please raise your hand. Mukesh, are you there? Okay, sir. I will take the question from YouTube. I have one question related to the frustration, magnetic frustration. So I will read the questions. Sir, can you tell a little more about geometrical frustration in connection to multifarics?
Well, geometrical frustration or any other frustration can lead to a ground state, which leads to a ground state which can induce. Actually, the magnetic structure is very important. Okay, when you have a strong frustration, you will end up in a spin glass, or there are various possibilities when you have frustrations. You can have a spin glass, or you can have a spin liquid. Okay. Or you can have this kind of cycloidal spin structure or spiral spin structure in general. So if you have a very weak frustration, so it depending on, nobody talks about it right now, how much is the frustration, where is the boundary for all these things. Actually, it would be nice to look at the magnetic frustration index as you vary the frustration index. Then at low index, you can see this kind of incommensurate spin structure. That's what it is important. The magnetic frustration can give you different ground state, but what we are interested in multiferrocity is that we need this kind of unusual magnetic structure which can break the inversion symmetry and gives polarization. So that's what we are interested. But depending on the magnetic frustration, even if you have a very high strong frustration, it can change the crystal structure and undergo long range magnetic ordering, a collinear magnetic ordering. Okay, like that it happens in spinel system. Spinel system has a very high frustration index. So what it happens, that's called spin Yontaller effect. That means the spin frustration is large, it is not able to order, so it distorts the lattice so that it can minimize the energy. Okay, so there are various effects happens, but we make use of multiferrite community want to make use of the very weak frustration to have a complex spin structure that can induce multiferrite effect or induce ferroelectricity. I hope you got that point.
Hello.
Yes.
Sir, you have some points you have not covered in your presentation now, sir.
My all slides you mean? What do you mean? I did not cover.
Please ask what you want to know. Because in one presentation, it is not possible to cover everything. Sir worked a lot in this field.
Yeah,
so
I can give series of talks because there's so much is there.
If you have any specific question, please ask.
Okay, can I get this presentation afterwards, sir? Whatever the presentation you have showed in this lecture.
You want presentation? I can give you some part of it.
Sir, let me answer. See, this video is available on the YouTube link which we have shared to you. So if you want, you can download that.
It's a huge file.
But the presentation of the fully is not been covered in that now. So that's why I'm asking.
Actually, whatever presented, if you take that is enough, because still, I may have still too many things which is not covered. It's not possible. Don't worry about that. But I have given one example for linear magnetoelectric. I have given one example for multiferroic with symmetry, magnetic structure, and that too from the same family of compound, an orthorhombic green phase. It's a very good example. In fact, we are very fortunate to get such effect in the same family of compound. So it is interesting. That is enough. You can apply the same principle to anywhere, any compound.
But I want to add actually, sir added very important information. And for the newcomers who are new in this multipheric measurement, for example, pyroelectric measurement, sir made very important note that while measuring the pyroelectric current, you should be very curious. You should be very attentive, and you can get the pyroelectric current due to the leakage also. So you must know how to perform the measurement. And sir mentioned that if you apply the DC magnetic field, which only few people are doing, so it is really very informative things which sir has shared with us. So I request other participants to ask the question. Okay, so I do not find any other question. If Rajesh, do you have any other question, then we will ask. Otherwise, we will thank our respected speaker for a nice presentation. Vedehi, is there any question on YouTube? Sir, we do not have more questions, but I really enjoy this session. I think all other participants are also enjoyed, as you have explained the magnetic point group especially.
Yeah.
People are talking about crystal structure point group, but only few people are talking about the magnetic point group.
Exactly.
Yeah. And your this green phase system is also very interesting.
Very interesting. Yeah.
Just changing the rare earth, you see that one material, the magnetic structure changed and it become magnetoelectric to multiferric.
Yeah.
So sir, with these words, so once again, I am really very much thankful to you for sparing your time from your busy schedule and deliver and this informative talk at this short-term course on advanced energy materials. And sir, I request you to come at NIT Jalandhar as soon as the things will become normal. So we are really grateful to have your talk here, sir. Thank you, sir.
Thank you, Professor Kiran, for nice arrange. I hope it will be useful because I myself, struggle to learn from the beginning because I should tell people, people should not think that we learned everything and coming. So everything we burnt our fingers and learned. Okay.
Yes.
So it's a very complex, and you can see how interdisciplinary it is. Okay. You need to know chemistry. You need to know physics. You need to know, magnetism very complex, and the symmetry, crystal structures, crystal symmetry, and magnetic symmetry, and measurements. It's all challenging, but I'm very happy that at the end of the day, you have learned something, and yeah, things are good. Thank you for the opportunity.
Yes, sir. I must say here, sir, that thanks to multiphysics, that it forced the people to understand the magnetic structure in more detail.
Correct.
Because sometimes after this is the field in which that if you have the result in your hand, then you can look for the solution of the magnetic structure.
Exactly.
So again, sir, I thank you very much again from the Department of Physics and from myself as well as organizing team. Thank you, sir.
Thank you. Bye.
Yes, sir. So, my dear participants, thank you very much for your patience, and don't worry about the attendance. We are here to learn something, not only for the attendance. So, I will send you the feedback link by your email, as I said yesterday, and please return your feedback, and I will consider that your attendance. Thank you very much. See you tomorrow at 10:30. Please join up to 10:15. Have a great day ahead.
Thank you, sir.
Thank you very much.
Thank you, sir.